Testing, testing. Okay, everyone, it's 1:01. Just letting some people have time to get in here. I'm going to start this real quick by showing everyone my class roster. Oops. I don't know if you can see this. Is there anyone who does not see their name there? Try and make it a little bit bigger. Anybody who does not see their name?
I don't see my name.
Jesse, did you register late?
Yes, sir.
Okay, all right, I'm going to add you here. Okay. I think that accounts for everyone because there's 18 of, well, maybe not. Anyone else that doesn't see their name? Caitlin,
No, I see it.
you are there? Oh, there you are now. Okay, I'm just trying to see if maybe I'll update my roster. I just for today, I want to make sure I have everyone accounted for. Okay, well, welcome to Calculus 1. My name is Robert DiGiovanni. I'm the instructor for the class. We're going to spend the first, hopefully 20-30 minutes tops, just going over the basics of the class. And then we'll get into material. We have a lot to cover even today on day one. So to start off, I hope that everyone has been able to get to Canvas, which I'll show you how to get there just in case. I'm assuming everyone, if you're here, that means you probably have already been here. So log into ACES, and then once you get here, you go to your courses, and here we go. So this is our main page for our class. And first things first, communication. All communication between me and you needs to take place here in this Canvas shell. And there's an inbox here on the left. I'm sure you can figure out how to use that. So just don't send me emails through your Gmail account or Yahoo. I most likely won't get that. So if I send you something or I say, hey class, I'll email it to you, or hey, send me something through email, this is where I want it to happen. All right. Now, in terms of this main page, let me switch over to student view. This is what you should see when you come in here. And I'm going to just go through a couple of things here, important things. First of all, the meeting information, you're here, so you already know this. Here's where you click to go to our meeting for Zoom. And then everybody, by being in this class, you've already paid for access to an electronic version of the textbook that this course is based off of. So if you click here, this will take you to a separate website. You put in this class key and you can register there to get access to the electronic version of the book. I'll show you briefly what that looks like. Whether or not you use it or not, that's up to you. So let me get in here. I just wanted to show you what it would look like from your perspective if you go in here. So you have to get registered. Is there a question?
Yes, sir. So strictly Canvas, you don't, I mean, the student email wouldn't work. You want it through the Canvas inbox only?
What email? What are you talking about?
Like the student email through the Outlook. So like it's like for mine's cmangold6@student.alamo.edu. And it usually works, but if you prefer Canvas, I can use that only.
Yeah, pretty much all courses are supposed to require Canvas. Like that's our official means of communication. Because if we do anything different than that, the system filters stuff automatically and I don't get things and then it creates problems. So, okay, so let's see. See if I can find you. Okay, it looks like a couple of you have already registered. That's good. Let me go to this class. This is what it will look like for you, something like this. And then in the bottom right-hand corner is a copy of the book. So that's where you can open up the book if you want to read through, you know, definitions, theorems, things that I'm referring to. The sections that we're covering are all connected to this ebook. All right. Now, everybody has free access to that. So yeah, there's not a whole lot more I want to say about that. We have a schedule that you can download and print that'll show what we're doing every day. And this also includes what your homework assignments are. Now, for the homework assignments, actually, you do need the ebook. I'll show you this. Let me bring up the schedule. So for each day that we meet, we have the sections we're going to cover. Let's zoom in on this a little bit. The sections we're going to cover, and then the homework assignments. So for example, your first assignment is 1.3, problems 4, 5, 6, 7, 8, 9, 13, all these problems. So the way you get to those problems, if you don't actually have the book, which you don't have to buy, is you go to the electronic book, you go to section 1 or chapter 1, and let's see where we start here. There's a little drop down here. You can go to, let's see, 1.3 exercises. Click on that. And then here are the problems that I'm asking you to do. So let's see, what was it? It was it's problems 4, 5, 6, 7. So I'd be looking at problem 4 here, problem 5, problem 6, 7, so on and so forth. So you'll need access to the electronic book to do the homework, but you will do the homework, you know, paper and pencil, you know, at home. You're not submitting anything online. The reason for that is that I actually provide you with all of the answers. So if you look down here, I have the homework solution videos. So if you click there, this is me working through all of those homework problems. So each section has its own video, and it's me.
Good grammar and
I should say
spelling.
something about this. So YouTube just changed its policies on advertisements. It used to be that if you were doing educational videos, then they would not put ads in your videos. They've changed that now, and they're just basically putting ads wherever they want to put ads. So unfortunately, there's nothing I can do to stop that because it's YouTube, right? So I apologize ahead of time that there's going to be ads. there's other options we could use other than YouTube, but it would be, I think, cumbersome, and I think everyone's comfortable with YouTube, and we can sit through 5 seconds of ads. Maybe, I don't know. I'm pissed about it, but just be prepared for that. But let me just let this ad play out. And it'll just be me on a whiteboard working through the homework problems. Okay, so there we go. You get the idea, hopefully.
So we have no homework assignments to actually submit. It's just, I mean,
That's right. So this is, it's calculus, right? So at this point, everyone here should know that the only way you're going to do well is if you do your homework. And so the homework is there to, to help you learn, and the video solutions are there to guide you if you get stuck. And remember, on these videos, you can always play these videos a little faster or slower if you want to. If you don't want to sit there and watch an actual 45 minutes of me doing videos, speed it up or whatever. Now, be careful, because these can be used incorrectly. All right. Students will say, well, I'm not going to do the homework. I'm just going to watch him work through the answers. And if it makes sense to me, then it makes sense. Then I won't need to do the homework. The problem with that is, when you watch me do a problem, I know the direction to go, right? So like, I'm making all the decisions. You're just following me through those decisions. And so, working your homework the way that I suggest you do it is try it, maybe have my video up and kind of like pause, play, and just kind of like see if we're on the same page as we go, as you're moving through it. But don't just watch and be like, yeah, got it, understood. That's just not the way math works. I mean, if you do it that way, good luck. Students don't usually have success that way. So, all right, so let me see, back here. I went through this homework solution videos, and then the Zoom class lecture videos. That's what we're doing right now. Everything on my screen, is being recorded. And so I will upload this to YouTube later today or tomorrow. And so you'll always be able to go back and watch what we're doing here on Zoom. All right. What else? Files. Okay, this is important. If you click on files, this is where I basically put everything for the class. And there's some important things here that you will need for your exams. There are the formulas right here. You click on that, and it's 6 pages of formulas. You're going to need to get a hard copy of that. So between now and the first test we have, if you don't have a printer, you're going to have to find somebody who does, or I don't know, go to Office Max or something. You need to print out the formulas, because on the exam you're allowed to have them, but they have to be hard copies. You can't be looking off your computer screen during the exam. So the formulas, there's also this thing called a limit summary. You can print that out. And then the this related rates worksheet. Now, you won't need that till later, but those 3 things: related rate worksheet, limit summary, and formulas. Those 3 things you print. Everybody can have those on the exams. The schedules here, I already showed you the schedule. Course notes. So as you'll see when we get started here, I use a program called Mathematica. I know everyone here has probably heard of Wolfram Alpha, right? The website Wolfram Alpha. Well, Wolfram Alpha, the brains behind that website is a program called Mathematica. And so I've been using Mathematica to create lectures, lecture notes, and visualizations for years and years and years. And so you'll see me working through these, notes. And there's like animations and things in here, and all of those notes are available to you in a PDF format in this folder. So if you click on that, you will have all the notes that I'm going to cover for the entire semester, chapter by chapter. Feel free to print those out if you want. You don't have to. This is only 15 pages, but if you wanted something to follow along during class, this is what I'm going to cover. Okay. So that's in there. And then there's some old exams and reviews. I actually don't even know what's in here. So these are just some old exams. In no way, shape, or form am I telling you that your exams are going to be exactly like these, but these are just some old things I have in here. Any questions up to this point?
Yes, sir. It's
Um,
not, oh, go ahead.
Sorry. For the exams, are we allowed to use a graphing calculator on them?
Yeah, I'm going to talk about that on the when I get to the syllabus. I'm going to run through the syllabus pretty quick, but I will address calculators.
Okay,
Cody?
thank you.
My question was for the exams, just some kind of a little bit more of a clarification on your camera requirements. Because I'm gonna
Yeah,
have to have some kind of jank setup depending on if you have to see my monitor as well and all that jazz. So
yeah. Again, when I get to the syllabus, which I'm about to do, I'll cover that.
thank you, sir.
Okay. All right, so let's get to the syllabus because the syllabus is the agreement. This is the contract between you and me, and basically we can't deviate from this unless it's explicitly stated somewhere. So here it is. I know you can all read, but I'm just going to hit the highlights here. When we meet is here. My contact information. The most important thing here is that I make myself available to you by giving you my cell phone number. And that number right there, you can reach me, you can reach out to me anytime you want. I may not respond depending on what I'm doing, right? But don't feel bad at 11 o'clock midnight to reach out. If I'll silence my phone, so you're not going to disturb me. But the main purpose of this is so that you can get immediate feedback if you're stuck on something. So what I recommend you do is first time you ever text me, just make sure you put your name, what class you're in, and then just send me a picture of the problem you're working on and the actual work that you've done on it so far. So it's important that I see the problem you're working on. Don't just say, hey, I'm having trouble with number 7 on the homework, because then I have to figure out like what section are you in, what chapter, just send me a picture of the problem, and then I can give you feedback. I have a phone that has a stylus, so I can write on it and edit, and just kind of like circle your mistakes, or if I need to work out the problem myself, I can. So just know that I'm available to you whenever you need help. All right. The other thing are office hours. So I do have in the summer, office hours are a little limited. So I have Monday, Wednesday office hours and Tuesday, Thursday office hours. Before this class, I'm available for an hour. And then on Monday, Wednesday, I have different office hours. And those are just Zoom sessions. You just go join, and there's a password for the Zoom session. These are the same Zoom sessions for Monday, Wednesday, and Tuesday, Thursday. It's the same Zoom session. So that means you can just join, during those times and just come and ask questions and get clarification or whatever it is you want to do. Just keep in mind that all my other students have that option also. So I might have some other students in there. If you need to meet with me on Zoom at a different time, different day, best thing to do would be just text me and say, hey, are you available today? And then I can work that. I mean, since I'm working from home, if I'm home and I have time, I don't mind just jumping in my office and jumping on Zoom to help you if I'm free. Okay. So just reach out for that help. Okay. The materials, like I said, you don't need to buy anything. Let me grab my book real quick. Okay, so this is the book that the class is based off of. If you're one of those people that really like to have like a book in your hands to make you feel like you're taking a class, then we've had this book for a long time. So I'm sure you can find it really cheap used somewhere. And all the information there to get the book is there. But remember, it's not required. All right. And we use that book for Cal 1, 2, and 3. So if you're at Northwest Vista and you're planning on staying at Northwest Vista for a while, you can actually take 3 calculus, the entire calculus sequence out of that one book. So it's kind of worth the cost if you're going to be taking all of them. I'm guessing you can get that for like $40, I'm guessing. Right? Has anyone tried?
I found it for 20.
20, yeah, I mean, that doesn't surprise me. Probably has like blood in it, but tears and blood. But
Just curious, did you have to still pay for the online version as well? Because it was kind of like part of the tuition or whatever?
it's included, it's included in the tuition, like access to the ebook. Yeah, so that's one of the things I don't like about what they've done here with this everybody paid for access to that ebook. So you didn't have an option, like it was included. I don't like that, because if you have a copy of the book already you got for 20 bucks, why should you have to pay for the ebook? But that's not my doing, right? That's beyond my control. All right. Yeah. Okay. Course description. I'm not going to read through this because you can read, and if I read it, you won't know what I'm talking about because you haven't seen this stuff before. So, but we do have objectives and outcomes that we need to achieve in the class. You have to remember that Cal 1, I teach Cal 1 as if you're taking Cal 2. I mean, that's the way I have to treat this class. I know there are some students that don't need Cal 2, but that doesn't make a difference. Like you have to look at this as if you did. Like I have to prepare you for that next step. And I'm sure some of you have heard that Cal 2 is a monster. Hopefully you've heard that because it's true. So Cal 1, you want to come out of this class as a strong student. Like if you're going to go to Cal 2, you want to come out of here like a B student. And even a B students struggle. I've had a student get an A in Cal 1 and then have to take Cal 2 3 times, because it was so hard for them. So just be aware that I have, my main goal is to prepare you for the next level. Okay. So I'm going to try and get through all these topics. All right. And then in a summer, it's going to be challenging to do. All right. So here we go. Standard grading scale, A, B, C, D, F are my only options at the end of the semester. And the way the grade is going to be broken down, exam 1, 25%, exam 2, 25%, final exam, 35%. So these are pretty heavily weighted exams. And I'm actually going to give you homework and quizzes 15%. I wasn't going to do that, but because there's no way for me to easily grade homework, there's no way, even quizzes are hard to do Zoom, because how do you turn them in, and how do I know you're working and not just cheating, and so it becomes problematic. But I didn't want you to just be like the whole grade is exams. So what I'm going to ask that you do for the homework is that you keep kind of a binder together of all your homework for the semester. And then what I'll do is one of the days at the end, what I'll do is I'll say, okay, I'm going to be checking homework today, and everyone's going to just kind of like show me their homework on their video, and I'll give you credit. Okay. Quizzes, I am going to figure out a way to do quizzes, but most likely they're going to be not during our Zoom sessions. They're going to be just like a take-home quiz that you'll have to submit your answers somehow. And I'll explain that, as we get to that. But hopefully that makes you feel a little bit better about the exams not being like all or nothing. You have a little bit of your grade is just doing what you need to do to stay on track. The final will be cumulative, meaning that it will cover it'll be heavily weighted towards the stuff at the end, but it will include stuff from the entire semester. But Cal 1 is kind of like one of those things where you can't really do the stuff at the end of the semester if you don't understand the stuff at the beginning. So I can give you problems from the end of the semester that include concepts from the beginning. So it's kind of kill 5 birds with 1 stone. All right, attendance, this is Zoom. So I am going to be doing attendance. I have a roster. I showed that to you. And every day what I'm going to do is I'm going to be calling on you. Okay, so I'm guessing every day, every person will be called on at least 1 time during class. And that's how I will take attendance. And then I also have a report that I can get from Zoom that shows me who was there and how long they were there. And so I want you to be here because, I want you to learn. Uh-oh, where'd everyone go? Hold on, I lost everyone. Okay, I'm back. Okay, so I want you all to be here and to be able to ask questions and be able to have some sort of engaging experience. It's going to be tough. I mean, 1 to 4:30. Is that real? Is that really what the time is on this class?
Twice a week,
Who signs up for things like that?
desperate people.
Jeez, right? Okay, so, we have to keep this in mind that, Cal 1 in the summer, 8 weeks is doable. Okay. Cal 2 in the summer, 8 weeks, I hope you're not working. I hope you're not doing anything else, right? I mean, but this is doable. I mean, this is definitely doable. But you have to keep in mind that the way that math always works is you cover topics, you go practice, you do your homework, then you move on to the next topic, right? When you're condensing everything down into 8 weeks, we might be covering 3 topics in one day. So you really don't have an opportunity to master or even get decently good at one of the topics before we're already going to the next one, which requires that you understood the one from before. So there are some issues when you try and do calculus in 8 weeks. Let's just keep that in mind. So as I'm covering something, I might be like, hey, realize that we covered this earlier today. And so, I know you're going to struggle. So you need to do your homework to get kind of caught up. So yeah, it's going to be interesting. All right. So because I take attendance, you can miss twice. After you miss twice, that's the equivalent to 2 full weeks in a normal semester. So at that point, I can withdraw you from the class if I feel like you've missed too much. Any questions? All right, I put this up here earlier about the bonus. If you came in late, you may not have seen this. So, I'm really looking forward to the fall because it looks like we're actually gonna be back in a classroom. We've all been doing this for way too long now. And I know some of you enjoy this because, there's something to be said about being able to sit at home, not have to drive somewhere. You're there, you're done, you move on. But there's also a lot that's missing here. And one of the things is just that personal interaction. And that's why I want to offer you bonus. I can't require this, but I want to offer you the bonus to have your cameras on. And that doesn't mean they have to be on 100% of the time. If you need to, get up and go use a restroom or go get a drink or something, that's fine. You can turn your camera off. It's just like consistently, I'm seeing you most of the time on camera. It just makes a huge difference for me to be able to look up and see a bunch of faces. I've got like 4 screens here. So I have the one I write on, and then I have all of you in front of me. So yeah, it's better than just black boxes with names. So I appreciate that. I will keep track of that. And that's 8 points possible on the final exam. That's almost a full letter grade. So I'll give you half a point each day that you have your camera on, and we meet 16 times. So yeah. All right. So what about the exams? We have 3 of them, right? And maybe we should look at the schedule to see when those were. I have the schedule here.
Just
So-
for whatever reason, if we can't make the class for the attendance policy, do you want us to just like send you a Canvas email explaining why we can't make it, just if there's like an actual good reason?
Yeah, I mean, yeah, if you have a reason that you missed, that's okay. Just communicate with me. I mean, at the end of the day, I'm a human. I have life happens to me too. So communication is the big thing. It's what I'm really not wanting is just people who just don't show up and don't show up and don't show up and don't show up and then, come take a test and don't do well and then wonder why. So yeah, just communicate.
Okay.
Your first exam is on the 24th of June, right? And that's all we will do that day. I might change that. Depends on how we're moving in the class. We don't need the whole time for the test. So we may push some other material into that day. Let's just see how things go here in the first stretch. But right now, June 24th is our first exam, and then July 13th is our second. And then shortly after that, 2 weeks later or so, we have our final exam. So those are the 3 exams. So about those exams, how are they going to work? Now, this is all written down here, okay, but I'll just explain it in words. So everyone's going to come in here, and just like you are right now, I see you, whatever, I'm going to email everybody the test. And then once you get the test electronically through Canvas email, you will have two options. You can print it if you have a printer, or you can copy down all the problems by hand. Those are your two options. Once you have printed or copied the test, you will then send me a message in Canvas saying, I'm starting the test. Okay, and at that point, when you start the test, I will require that you change your camera so that I can see you. So what I want it to look like is kind of what it looked like here on our homepage. That's why I had a picture of myself. It wasn't just to have a picture of me. It's to show you an example of what your camera should look like. So your camera needs to be far enough away from you that I can see that it's you, but also see your entire workspace and what's in front of you. So I need to be able to see this. Like that way, you know, you don't have like a wall covered with formulas and worked out problems everywhere. You know, got this big old collage of Cal 1 stuff all over the wall. I want a fair playing field for everyone in this class. You know, if we've got a couple of people who are cheating, well, I don't want that. So you've got to have your camera set up this way. Now, how do you achieve that? Well, if you have a laptop, you can just move your laptop around your room and get yourself positioned. If not, I just suggest you use a phone and just download the Zoom app on your phone and just set your phone up, you know, somewhere near you. And that's going to take some practice for you to get this to set up properly, and make sure you plug your phone in so it doesn't die in the middle of the test. And then you'll start the test. Does that make sense?
Just clarification, we would, I guess, respond to the email in Canvas, or would we send something
No.
in Zoom?
In Zoom, you would send me, after you printed it or copied it down, you would send me a chat in Zoom saying, hey, I'm going to start the test now.
Okay.
Because some people are going to finish, you know, like some people are going to print it out and they're going to be ready to go, and then other people are going to be copying it. And some people can copy slow and fast. I don't want to make people wait on other people. So as soon as you're ready, you'll send me a text saying, hey, I'm going to start the test. At that point, your camera needs to be set up and ready to go. And then you take the test. All right. And you're going to be paper and pencil, everything. There should be no computer screen. See how I have a computer in front of me? That would actually need to be off during the test or moved out of the way. All right. If you do have a computer screen in front of you, just turn it off. All right. And I just need to be able to see what you're doing. Paper and pencil, take the whole test. When you're done, you will send me another chat in Zoom saying I'm done. And then at that point, once you say I'm done, you have 15 minutes to leave the session and somehow convert all your handwritten work into a single PDF file. Okay, so if you don't know what a single PDF file is, you're gonna need to figure that out in the next day or two. So I recommend, if you don't have a scanner, that you take pictures. Okay, and if you're using an iPhone, I believe the notes feature in iPhone allows you to take all your pictures and turn them into a single PDF file. If not, there's an app called Cam Scanner, like camera, Cam Scanner, and that will allow you to take pictures and then put everything into a single PDF file. That's the most important thing. I want one file from each student, and you'll send that to me. And you'll send it to a Dropbox link that I will send you. Before class started today, I sent everyone an email in Canvas with a Dropbox link. And what I'd like for you to do is, by next class, I want you to send me a single PDF file with multiple pages in it. So I want you to practice. Just take pictures of whatever you want to take pictures of and get that all into a single PDF file and send it to me. That way you know how to do it and you're not trying to figure that out for the first time during exam 1. Because if you don't get me your work in 15 minutes, I won't accept it. No, and there will be no exceptions to that. Because it's just not fair to give up someone more time than others. So does that make sense? What I want from everyone the next day or two? And if you're getting, if you're having trouble, just let me know, right? Reach out to
Does Dropbox have, oh, sorry.
Say again.
Does Dropbox, like whenever, you said you use Dropbox, right? I have Dropbox too. Is there a way to make it a single PDF on there as well?
I don't think Dropbox will make a single PDF, but I could be wrong.
Okay, yeah, I don't remember it doing that. Okay.
I'm not aware of that. So you need, go ahead.
There's Adobe Scan for iPhone users. You can just download that app and it'll make it all into like one single PDF.
Oh, sweet. Thanks, Nathan.
Yeah, there's a bunch of different ways to do it. I don't have an iPhone, so I can't, and I know most of you do probably. But does anybody use Android?
Nathan, what did you say it was called? Adobe Scan, right?
Yes.
Okay, cool. Thanks.
Yeah, if you're using an Android, I use something called JPEG to PDF. JPEG to PDF. I'll write this
I think
down.
my last one I used was Genius Scanner. So
Yeah.
I'm trying to find it right now. Yeah, Genius Scan
Yeah,
is the
there's
last one I used.
There's a bunch of them out there. The thing is, you all need to figure it out. Okay, and we'll take, the next day or two for you to do that. And let me show you an example of what I should get from you. Okay, so I'm going to show you something from the spring that a student sent to me. I'll do my Cal 3, that way nobody, you look at it and you won't, this is actually a test. So here's a file. So this student sent this file to me. It was 5 megabytes. Okay, and here's how it came. When I open it, this is what I see. Isn't that pretty? See how
Nice
neat that
handwriting.
is? Now,
Like my checker's wrench.
neatness is something else. Okay, I mean, I understand some people have trouble with neatness, but look at number 1 is the first page. It's upright, right? It's not sideways, upside down. It's not like I can't see. It's not blurry, right? And after number 1, I'm guessing number 2. Yep, number 2 is next. See, I mean, that stuff seems simple, but these things make a difference when I'm trying to grade 20 students' work, is to have everything nice and neat and in order. So this file is 12 pages. I don't know if you can see it here, but it's 12 pages of work, but it's a single file. If this student would have not done that, then I would have received 12 files, right? And 12 times 20 students, it gets to be a disaster for me to manage. So what I will do is, once you send that to me, I will grade it. So I have the ability to write on it on my screen. I'll grade it, and then I'll make a copy of that and send it to you. So you'll actually get an electronic graded version of your test come back to you. All right. And that's the way the test will work.
Is it all right for the Dropbox if I just send you one of the big PDFs I made for my last math course?
Yeah, as long as you know how to do it. Yeah, if you're comfortable with it, send me something from before. But just, I mean, don't send me something. I've had students send me like files that are like 125 meg or something. I'm like, whoa, it should never really go over like 8 meg. I mean, so just be careful. Don't send me like 80 pages worth of stuff in one file.
Yeah, my math lab turn-ins for my pre-cal class were pretty rough.
Mhm.
It was like 56 pages at one point.
Yeah. Okay, so that's the way the exams are going to work. And that's pretty much it, for the exams. Are there any questions on that? All right, the rest of this is just administrative stuff, behavior, and tutoring. Just be aware, remember you're on camera, like just remember what's in your background, what you're wearing, what you're doing, right? Because everything gets recorded. Shoot, I'm the one who has to worry the most about that, but please do. I won't even talk about it. Okay, so that's it for the syllabus. At the end of the syllabus, it does have your schedule, but I think you should print out that version of the schedule that looks like this. Just print it out and have it with you. All right. So, ready to start? I feel like I'm missing something here.
Yeah, the calculators, sir.
Yeah, I never talked about it, did I? I just blew through that. Oh, it's under required materials. Oh, I did not put that in here. Huh. Where's my calculator policy? I'm gonna have to update it. I thought it was in there. It should have been in there. Okay, so calculators, all you need for the class is a scientific calculator. Okay, so that's the minimum requirement, is scientific calculator. Remember, during the exams, you can't be on your computer and you can't be on your phone. So you actually need a calculator for the exam. So I guess what I'm getting at is I don't want you to get used to using your phone or using a website to do all your calculations. And then come the exam, it's like the first time you picked up your calculator and you don't know how to do certain things. So scientific is the minimum requirement. You may have a graphing calculator, but there are some restrictions on the, like how advanced your calculator can be. You're not allowed during the exams to have a calculator that has a computer algebra system built into it. That's called a CAS. And there's only a few calculators that do. The TI, Texas Instruments, the TI-89, the TI Nspire CAS. Now be careful because there's two Nspires. One of them, it'll say it on the calculator on the top right-hand corner. It'll say, I have the one that's not CAS. So let me see. I never used this thing. Yeah, so mine says, I don't know if you can see that. It's hard to see. Mine says TI Nspire CX. That's okay. But this, if it says CAS on it, then that's not okay. And I don't know if there's, oh yeah, no, that one's obsolete. These are the only two I know of that you cannot use on the test in the class. And that's because they do symbolic manipulation. They basically do things like what Wolfram Alpha and stuff does. You have to learn how to use it, but it's kind of too much, all right? So you're not allowed. And moving on in your college life, most courses won't let you use those on tests. So it's not worth you getting used to. All right. Questions? All right, so y'all are ready, huh? Get into this.
I don't know if I go that far, but we're gonna do it.
Okay, so let's do a quick little discussion about, the things that you need to know coming into this class, all right? So, math, and when I was a student, I thought this too, that math is very linear. Like you start off with, elementary school and you learn addition, subtraction, multiplication, division, then you start learning some pre-algebra and then algebra. And everything is just, you take one course, then the next one, then, it's like one foot in front of the next, right? And then you just keep moving down this path of math. And that's the way math is for a while. So you've moved, let's just go back as far as college algebra. Everyone here is taking college algebra and passed it. And then after that, you moved on to pre-cal, right? And now you're in Cal 1. And if you were to continue, then would be Cal 2, and then Cal 3. And then at this point, you actually would be able to branch out and you have options as to what math class would come next. Okay, so once you get through Cal 3, then there's all these different concentrations in math that you could go down. There's differential equations, there's topology, there's analytic geometry, there's a bunch of different paths. So I always thought that math was just, you just take the next course, right? You just keep going, but no, it actually does branch out at some point. But we're still back here. So I'm trying to prepare everyone for Cal 2. This class, the things you're going to need to know from algebra and pre-cal, well, there's a ton that you need to know, right? Everyone here needs to be comfortable with factoring, with, algebraic manipulations, properties of exponents. There's a lot. And then in pre-cal, the main two things from pre-cal, the biggest two things that you need to know from pre-cal are the unit circle and then solving trig equations. We will see that almost immediately in this class, that we're going to be pulling on stuff from pre-cal. Those are the main ideas from pre-cal. So everyone here is going to be at a different level depending on your background, you know, how strong you were in pre-cal. I would say though to you that pre-cal really isn't about the math. Okay, like the reason this class is called pre-cal isn't really about the math in that class. There's a lot you did in pre-cal that we're not even going to talk about here. But it's pre-cal is supposed to get you prepared like mentally, like maturity wise, like your mathematical maturity level should be much higher at the end of pre-cal than it was at the end of college algebra. And so coming into this class, you know, your the level of which, you know, like the peak of what you can do, each time you go through another class, that bar should be raised up a little bit more, a little bit more, a little bit more, so that you realize, wow, I can do more than I thought I could do. All right. So in Cal 1, we raised the bar a little bit. But the thing in Cal 1 that's I think you're going to see is that the thing that gets people in Cal 1, anybody have a guess as to what people struggle with in Cal 1? What it is that the Achilles heel of Cal 1 students?
Basic algebra.
It's the algebra.
Yeah, my pre-cal professor mentioned it.
The algebra. So it's all the little manipulations that you have to do to get the Cal problems to work out. The concepts, the ideas in Cal 1 are not that crazy. Most people can understand them because they're very visual and they go, oh, okay, yeah, I see that. But then actually making it happen with the algebra is the part that becomes a problem. So just be aware of that as algebra starts to peek its head out here and you start to feel a little weak and wobbly, you know, that's pretty normal, but you need to make sure you fill those gaps and get clarification and help. Don't wait till it's too late to ask for help. Okay. Oh, I know I forgot something here now. The tutoring lab. Did I put the tutoring lab in here? Yeah. Okay. So when I'm not available, if you want to get help in this class, the college has a Zoom link you can click on here. This is in our syllabus. Here are their hours of operation. You should be able to click on that and get in there and get help. Just tell them you're in Calculus 1 and they'll hopefully be able to find you a tutor that can help you. And that should be like a one-on-one. I don't know how it'll be, but they've been telling us to let everyone know about tutoring, you know, because they need people to get in there and get help. So yeah, go get help if you're having trouble with something, if I'm not available. All right. So I've laid out kind of that we are going to be pulling on some things from the past, but what is Cal 1 about? Like if I were to try and say like, what's the main idea behind Cal 1? If I could like try and summarize it into like one idea, here's what it is. All right. Let's say we have a graph of a function. Right? If I pick any 2 points on that graph, any 2 points, I can connect those 2 points with a straight line. Right? And that would be called a secant line. That's what we call it. Okay. Right. That right there actually shouldn't be a problem for anyone in this class, because if I were to give you this point, let's call it x1, y1, and I were to give you this point, x2, y2, everyone in this class should be able to give me the equation of that line by using the formula y minus y1 equals m times x minus x1. Now, maybe we would need to work through an example to convince you that you've already done this in the past. But finding the equation of a line given 2 points is very easy to do in college algebra. Okay, 2 points, equation of line, thumbs up, we're good. Cal 1 is about, is it possible to find the equation of a line on this graph that is tangent to the graph at a single point. So for example, if I pick, let's say this point right here, that single point, can I find the equation of a line that would just barely touch that graph at that single point? So notice it's what we call a tangent line. And when you think of tangent lines, you can go back to a circle. If you have a circle, then a tangent line to a circle is a line that touches the circle at one point. And if you were to connect it to the center of the circle, you would have a right angle there. So it's perpendicular to the radius. That's what a tangent line is on a circle. But in calculus, when we look at a function, this is a question, okay? Can we come up with the equation of a line that just touches our graph at a point, given any point on the graph? Can we find tangent lines or not? Or the equation, can we find the equation? Sorry, the equation of that. That's the question, can we do it? And immediately there's major problems, because in order to find the equation of any line, you need 2 points. So if we're talking about finding the equation of a line that only passes through 1 point here on the graph, we already have an issue that we only have 1 point, not 2. And so we're going to see that this is going to be a problem, but that's the main idea in Cal 1 is, can we do this? Now, let's say that we can. Let's say that we figure out a way to do it. What does it allow us to do? So imagine now that if I give you a function, you can find the equation of the tangent line for any point on the curve, okay? Imagine you can do that. Then you would have this scenario. Let's take this, a new graph here, new function. Okay. So in college algebra, when you were studying functions, this looks a lot like a polynomial, doesn't it? Those things that go up and down, up and down. When you're in college algebra, are you ever asked in college algebra to find the highest and lowest points on a graph?
Max and min, I can't remember if that was algebra or pre-cal that we went over that.
So in algebra, when you're studying polynomials, things that go up and down like this, think hard about this. Were you really ever asked to find these highest and lowest points?
Weren't you supposed to find just the lowest and then the highest, not like each individual?
The max and the min.
Well, we could find the highest and lowest points on a parabola. So if you go back and think in college algebra, like if somebody gave us a parabola, then we could find that highest point. And if it happened to open the other way, then we could find that lowest point. We called it the vertex, remember? And we had a formula to get it in college algebra. But if you think back, if you were to go back and look at your college algebra notes, once you got past parabolas and started talking about polynomials in general, we stopped asking about highest and lowest points. What we did find were x-intercepts. We did figure out whether or not we had like bouncing or crossing on the x-axis. Those were called multiplicities of roots. I don't want to get too technical here on the first day, but if you go back and look, in college algebra and pre-cal, we never talk about how to find the highest and lowest points on a graph. In general, we don't. And the reason we don't is because it's difficult to do without calculus. In fact, you can't do it without calculus. So why is it that we should be able to do this now? Well, look at all of these points. Imagine the tangent lines to each of those. Wouldn't the tangent lines all look like this if I were to draw them? Wouldn't all those tangent lines be flat? So what is the slope of a line that's flat, horizontal? What's the slope of a horizontal line?
0.
0, right? So what we're trying, if I wanted to know where do these things happen, right? Where do we get these highest and lowest points? Then what I want to know is when is the equation of that tangent line have a slope of 0? If I can figure out where the equation of the tangent line has a slope of 0, then I can identify all of these points. Okay, now I have to speak abstractly right now because we haven't defined anything yet. We don't have like good language for all this yet.
Just a
But the
question.
general idea. Go ahead, Cody.
Is this going to have something later? Maybe not this exact scenario you're describing here with the slope of 0, but isn't this going to have something to do with difference quotients at some point?
Absolutely.
Okay, because I remember my knowledge professor telling me about it. You want to get the h to 0 because you're trying to find the closest 2 possible points or something like that.
That's exactly right. So we are going to get to this by the difference quotient. The difference quotient is going to get us there, which is why you study it in college algebra. Okay, so now I started this whole conversation off saying the goal of Cal 1 is to try and see if we can come up with the equation of a tangent line on a function. I said, if we can figure out how to do that, then does it seem reasonable that we should be able to figure out the highest and lowest points on a graph?
Mhm.
Yes?
Yes, it does.
Okay, so now let's assume we can do that. Assume that if you give me a function, I should be able to find the highest and lowest points. Then what kind of, how is that useful to us, right? To be able to find the highest and lowest points on a graph. I mean, who cares, right? Well, imagine this. I'm going to throw this together real quick. Imagine a scenario like this where I had a road. Okay, we're looking from the top, and I had some building over here. I'll call it building A, and I have some building over here called building B. And let's say that these buildings were 1,200 feet down the road. Okay, so building A is here and building B is 1,200 feet down the road. Understand? And I want to pay a company to come out here and connect these two buildings with fiber optic cable. Right, so I'm going to pay somebody to connect these two buildings together with a cable so they can communicate with each other securely on a fiber optic line. So when I connect these, I have a couple of options. If I go and connect down the side of the road, I can actually dig and bury the cable, okay? But if I go underground on the side of the road, I can bury it. But when I go over the road, I can't go underneath it, okay? There's water down there, there's other things, other utilities, so I have to go over the road, understand? So when I go over across to B, I have to go, the green is over the road, okay, green is over. So this is gonna be underground, and then this one will be above ground. So the company that's gonna do this for me, it's going to cost them a certain amount of money to bury the cable, isn't it? And then it's going to cost them another amount of money to go above the road. Now, it depends on how they do it, but the cost for doing those two things, the yellow and the green, are two different costs. It might be cheaper to do this and more expensive to do this, or the other way around. So imagine that there's a different cost for each one of these scenarios, right? The yellow and the green. What would be a good question if you own the company that was going to try and get this bid to lay this cable? What would be the important question that you would want to answer?
How much cable do you need? Like length?
Okay, length. Well, length would be easy because the shortest distance between 2 points is a straight line, right?
True. Maybe the height of how high you need to have it above the road.
Yeah. Think about cost.
Yeah, the cost of each, the burying it and putting it above, the cost of each.
Yeah, so like if you own the company that's going to bury the cable, what you want to do is you want to figure out how can I do this the cheapest, right? What's going to be the least expensive way to do this? So the cost will be equal to the cost under the ground plus the cost above the ground. Do you agree? Whatever it is, it's those two costs together. Now, there are an infinite number of ways that you can do this. Think about this. Here's one way I could do it. I'm just going to show you one way. One way would be to connect these like that. And that would all be above, wouldn't it? Everything would be above ground, just boom, straight across. that's going to have a certain cost to it. I could go all the way, now that would have a certain cost, but isn't that that right there is the shortest distance, right? Okay, now I could go down like this and then straight across. That's another way I could do it, right? That's going to have a different cost. Or I could do some weird combination of the two where I go down and then I get to a certain point and then I go across. In every scenario in between is possible for you to do, isn't it? Does that make sense? So if you were to look at this as like X is how far down you go, and then this right here is your Y, is the distance you go across, then your cost is going to somehow be determined by the X and the Y, wouldn't it be? If there's a way to figure out this cost as a function of just X. So if we can somehow get this cost to be determined just by this distance, give me this distance, and then I'll tell you what everything else is. If we can do that, then that cost function has a graph, doesn't it? And if that cost function has a graph, then it's going to have a lowest point. And if it has a lowest point, it'd be nice to know where it is. And if I can figure out where that is, that tells me the X I need to go to make this as cheap as possible. And therefore, I can get a good bid in so I can get the job. That makes sense. If I don't care about the cost and I just throw a number out there, you know, without actually doing any work, any math, then I could lose the bid because I haven't optimized the job. I hope that makes sense. I mean, you can do this for anything. Anytime you have a graph of anything, if we can find highest and lowest points, that allows us to do a lot of stuff, and that's called optimization, which will be one of the main goals of this class, which you can see down here at the very end of the class. We will talk about optimization, but there's a whole bunch of stuff we have to do before we can get to optimization. All right. I've taken an hour to prep us, and now we're ready to get into it. Okay, it's 2 o'clock. We have 2.5 hours now. Jeez. Let's take a break. I would like to take a 10-minute break every class somewhere in the middle, which would be about I think 2:40 is when we would take the break. Are y'all okay with doing that? It may not be at 2:40 every day, but it will be somewhere around 2:40. All right. Okay, here we go. Let's start with the first section. Now, in a traditional 16-week class, I start chapter 1, and I do chapter 1, section 1. I talk about functions. I give you, I remind you about some things from college algebra, and then I do 1, 2, which would then also remind you of some important functions that you should remember from college algebra, you know, like quadratic functions and square root functions. And then we talk about sine and cosine, tangent, just remind you about all these different things. Because we're in 8 weeks, I have to start the class in 1-3 if we're going to make it to the end. So that's where I'm starting today, 1-3. So if you want, you can go back in the notes yourself and look at the 1.1 information where I talk about polynomials and, you know, different types of functions and piecewise functions. What I'll do here today is I'll try and fill the gaps in as we go. If you have questions, it's important you ask. Okay, so we're going to start with the limit of a function. So right away, first day, first topic, we are going to be talking about calculus. And this is the heart of calculus right here. Everything in calculus, Cal 1, Cal 2, Cal 3, all of it is based upon this concept of the limit. Right? So the first section, 1.3, that deals with the limit is very visual, which is good because I think we need visualizations to help us here. So there's a lot here. Don't worry about copying every single thing I have down here because you have access to all this. This is more about you trying to understand what you're seeing. All right, so I have here a graph And I want us to discuss the behavior of this function at x equals 2. Okay, so I have to do something here. There we go. Okay. So when you graph a function, y'all see this function here in red? When you graph a function, if I were to ask you, hey, what's happening at 2? Oh, I didn't show you what the function was, sorry. That's the function right there. Okay, f of x equals negative x cubed plus 4x squared. It's polynomial. If I ask you, hey, what's happening at 2? Okay, then what I'm really asking you to do is plug 2 into that function. So you just plug 2 in, let's see what happens. Negative 2 cubed plus 4 times 2 squared. And this is just arithmetic, right? This is negative 8. Let's see, 2 squared is 4 times 4 is 16, so plus 16. We should get 8. So if I hand you a function right now, right? Like if I hand you a function and I say, hey, what happens at 2? You plug 2 in, it spits out a number, right? That's what this picture is. Notice that everything is blacked out. Everything is blacked out except what's happening at 2. At 2, you plug in a value and it spits out 8. That's algebra. That's what algebra is all about. In college algebra, you're given a function, you can plug a number into it and see what the output is. That is not what calculus is about. Calculus is not interested with what's happening at 2. I'm going to say that again. In calculus, we are not interested in what's happening at 2. We are interested in what is happening near 2. So I'm going to now hide the middle from you. Okay, I'm going to hide that middle piece. And now I'm going to ask you, what is the function doing? Where is the function headed as you get closer to 2? Now, what I mean by that is imagine you are like walking on this graph. And you're walking, here's x is 2 down here, right? That's x is 2. What happens as you take values that are getting closer and closer and closer and closer and closer to 2, keep moving from left to right, getting closer to 2, where is this person headed? So,
Increasing,
To the maximum.
going up.
well, he's going up, right? But to what y value is he approaching?
8.
It looks like 8, right? Like, look at all these y values. Like here, the y value is like below 2. But as you keep moving to the right, the guy goes up. He's closer to 4 now. Here he's closer to getting close to 6. Here he's past 6. And the closer and closer this person gets to this point, right? To 2, the closer that red function gets to 8. Y'all agree with that? Y'all understand that? Any questions with that? I'll show it to you a different way. If my x value, which is in blue here, 1.4, gets closer to 2, watch how 1.4 moves closer to 2. Look at what the y value is doing. The y value is now at 6.1. Now it's at 6.6. I'm at 1.7 here. I'm going to keep going. 1.8, I'm at 7.1. 1.9, I'm at 7.58. At 1.91, 7.62. Let me get even closer. At 1.99, I'm at 7.95. Let's get even closer. At 1.991, we keep moving closer. At 1.99, wait, 1.999, I'm at 7.996. Right?
So it's almost asymptotic. It's just going to continually get closer.
It gets closer, right? As the x gets close to 2, okay, so I'm gonna try and write this down. As the x goes towards 2, so that arrow means my x is getting closer to 2, the function seems to be getting closer to 8, doesn't it? As x gets closer to 2, as x approaches 2, the function approaches 8. It looks like, right, from what we can see in front of us. Now, that's not the only way I can approach 2. I could have stood on this side of the graph and started marching my way this direction, right? So picked X values over here that were bigger than 2 and started to work my way to the from right to left. Now, what happens to the Y value as that happens? So I'm going to clear this out and let's come in from the right-hand side instead. So watch what happens when I come in from the right. My X value is 3.4. My Y value is up at 6.9. Now watch what happens here. It goes above 8, doesn't it? It goes above 8, but what's going to happen is I keep moving closer to 2.
Go closer to 8.
Coming back down, right? And now it's getting, oops, wrong way. 2.1, I'm at 8.37. 2.01, I'm at 8.03. So it's coming down, right? So from the left side, as I came in from the left, the Y value of the function approached 8. And as I came in from the right, the Y value approached 8. And if I ask you what's actually happening at 2, that's the college algebra question, your answer was 8, wasn't it?
Mm-hmm.
So if we recap that, this function's value at 2 was 8. As we came in from the left towards 2, it approached 8. And as we came in from the right side of 2, it also approached 8. So it's like all three things were doing the same thing. Now, you might be saying, okay, well, who cares, right? Like, big deal. Let's look at a different one, okay? Because they're not all going to behave like this. So here's the function that I'm giving you. This is known as a piecewise function, which means that it has two different pieces. It's defined to be two different functions depending on what X values you're plugging in. So I'll start with the algebra question. What's happening at 2? So if I ask you to plug 2 into this, let's call on the first person today. I'm just going to go in alphabetical order today. Okay, Cruz, are you here?
Yes.
All right, Cruz. If I ask you to plug 2 into this, are you going to plug 2 into the top function or the bottom function, and why?
Let's see.
So if I say replace X with 2, do you do it here on the top or the bottom? And if anyone, when I call on you, if you're not sure, just say, hey, I'm not sure. No one's going to care. All right. We're here to learn.
It would be the first. It would be. Wait, next. It would be
This one?
the first one. Yeah, the first.
Yeah, first one. And the reason is because we're plugging in 2, right? We're plugging in 2. And geez, sorry. I'm asking you what's f of 2, which means you have to look here or here. If X is 2, then 2 is less than or equal to 2. So we want to use this one. 2 is not greater than 2, right? So I don't use that one. So let's plug 2 in. Let's just plug 2 into this and let's see, what do we get? I think we get 8, don't we? If I plug 2 into this, that's the same problem we just did a second ago. So you get 8. So for this function, if I ask you to plug 2 in, you get 8, right? Does that mean that from the left it's going to be 8 and the right it's going to be 8? We have no idea, okay? We have no idea. We have to look at the picture to be able to see that. So what I'm going to do now is I'm going to cover up the middle piece and show you what the outside of this graph looks like. So if we look to the left now, see what the graph's doing, and then to the right, do y'all see that it's doing two different things on both sides?
Yes, sir.
So let's try and approach first from the left. If we try and approach 2 from the left, let's see where the function is headed. So visually, where does that look like that's headed, Justin? Closer I get to 2, what's the Y value getting closer to?
From the left, it's getting closer to 8.
It's getting closer to 8. Everyone see that? That's visual. Okay, that's strictly from the picture. Okay, Jorge, how about from the right? If I were to come in here and start approaching from the right-hand side of 2,
4.
what does it look like?
4.
4. Does everyone see that? It went up and now it's coming back down, and it looks like it's approaching a Y value here of 4. So that's a little different than the previous problem, isn't it? Previous problem, at 2 it was 8, from the left it was 8, from the right it was 8. This problem, at 2 it's 8, from the left it's 8, but from the right it's 4, right? From the right it's 4. So it's different. And I'm not saying anything about that yet, we're just trying to recognize that there's a difference. Let's look at the next one. I'm going to show you the function first. I'm not going to show you the picture. It's down here. Can you all see that down there?
Yes, sir.
Okay, so there it is. I'm going to ask someone first. This is the algebra question. What's f of 2? And that's going to be Brianna. Brianna, can you tell me what f of 2 is? Yeah, just tell me what f of 2 is. Is Brianna here?
Yeah, I'm right here. Sorry.
There you are, Brianna. Okay, so Bree, do you prefer Bree?
Yeah.
Okay, so I'm going to change that on my roster piece here.
Okay.
So I can call in. So Bree, can you tell me what this function would spit out if I asked you to plug 2 into it? So you're going to be in the top function, middle function, or bottom function.
To get 2?
If I tell you to plug 2 in, if I say x is 2, to use the top, middle, or bottom?
I'm going to say middle.
Middle, right? Because this right here, is kind of telling you the domain, like what piece to look at. So when I say plug 2 in, you have to check, is 2 less than 2? No. Here, down here, is 2 greater than 2? No. Is 2 equal to 2? Yes. So that means you're going to use this one. So Bree, the answer you said is 6, right? Okay.
Yes.
So what we know is that at 2, we should have a dot. This function should have a dot at 6. That does not mean from the left and the right that it's headed to 6. It doesn't mean that, right? It just at 2, that's what's happening. You already see the picture? Let's take a look. So you can see here that at 2, I have a dot at 6. There's 6. I have a dot right there. At 2, it's equal to 6. But now let me flip things around, cover that up, and let's look from the left and right. Something is happening. It's not the same as what's happened before. So let's see. Brian, yeah, Brian.
Huh?
From the left, what do we have happening? If I were to approach 2 from the left, where's the function headed?
Towards 8.
Towards 8, okay. And Rogelio, from the right, what's happening?
It's approaching 4.
It's approaching 4, right? So as we approach 2 from the right, the function's value is approaching 4. So now we have this scenario. At 2, it was 6. From the left, it's 8. From the right, it's 4. All these weird things that are happening here. Okay, how about this one? So here's the function. I don't want to give it away, so I'm just going to put it here. Hopefully y'all can see that. So here's the function. And I'm going to ask Gabriella what f of 2 is. So if I ask you to put 2 into this,
Would be 0.
Wouldn't it not exist because 0 over 0?
that's right. You're going to get 0 on top. Wait, do I have 2 Gabriellas?
No.
Okay, I'm sorry.
Mm.
Okay, so Gabriella, you got a 0 on top, right?
Yes, sir.
And then you also got a 0 on the bottom. Is that what you said? 0
Yes,
over
sir.
0? And 0 divided by 0 is undefined. Undefined. That means that when I look at the graph, if I go to 2 and look to see where a dot is, there is no dot. Okay, there should be no dot there. There's actually a hole in the graph there. If we plug in any other number other than 2, it should be okay. Well, -2 will have a problem also, but at 2, we definitely have a problem.
Question.
Yes.
Isn't that just because when you factor out the bottom, you can then cancel out the two factors, so then it creates the whole?
The fact that there's a factor common on top and bottom.
Yeah.
Is what creates the whole.
Right, okay. I just wanna make sure
Yes.
that was-
So in college algebra, when you're learning rational functions, you're taught that if you factor the numerator and denominator and they have a common factor on the top and bottom, that creates a hole in the graph. And that's what's happening here. But anytime you have 0 on the bottom, regardless of what's happening on top, anytime you have 0 on the bottom, your function will be undefined. Now, one thing you have to be careful with, let me bring something up here. There's some online graphing software called Desmos. Y'all heard of that before? I really like this graphing software. If I were to type in that function, it was 2 minus x over x squared minus 4. I think that's what it was. Here's the graph. Let me clear that out of there. Here's the graph of that function. What did we say was happening at 2?
There's a hole.
It was a hole. But look, I mean, according to this graph, do you see a hole here? Look, here's the x value 2, right? Do y'all see a hole?
No.
I don't see a hole. This is one of the limiting issues with graphing software, even your graphing calculator. They don't show you holes. Okay, so you may think that this graph is nice and smooth and you can just draw it without picking up your pencil. But in fact, if you were to try and draw this for real, you would technically have to leave a hole right there and then continue graphing. That's what you would have to do. So limitations of software, I'm just trying to point that out. Let's go back to this. So what Gabriella just said was that at 2, we're undefined, right? At 2, we're undefined. Now let's take a look at the graph. See, at 2, I left a circle there, an open circle, because it's undefined. Let's switch it up. Let's look at what's happening as we approach from the left and from the right. So I'm going to ask someone to tell me, but let me run it first. Let's approach from the left. Okay, so I'm approaching 2 from the left. Keep an eye on the purple number. Where does that look like that's headed? I'll take a volunteer on this one. I'm going to keep getting closer and closer. Anyone want to volunteer and tell me what it looks like that y value is getting closer and closer to?
-2.25.
Negative 0.25 looks like it's getting closer to that.
Yep.
From the left. As the x value got closer to 2, the y value looks like it's getting closer to negative 0.25. And from the right, let's see what happens. Coming from the right, keep an eye on the black value here. That's our y value. This is our x value. As we get closer and closer. Let me get the other one out of here. Negative 0.24999. So that again looks like negative 0.25. So this one is different than anything else we've seen already, right? Because at 2, it was undefined. We had never had that before. At 2, it's undefined. From the left, though, and the right, aren't they kind of headed towards the same place? Okay, I'm going to restate this one. This is the most important one. At 2, it's undefined, right?
Right.
But
Yeah.
from the left, it's headed to the same value that it's headed to from the right. This is a strange scenario, but this is actually what's going to eventually allow us to find slopes of tangent lines. Okay, this is what's going to do it. I'll explain when we get to it, but
Are we just trying to find a point that on both sides you basically have the same, you're going towards the same value or the same kind of maybe, I don't want to use the word slope because I know that that's kind of a red word in this class, but
okay, so let me try and explain what okay, let me do it this way. say we have a function, okay? And forget everything that I've just shown you with these pictures coming left and right. Let's go back to the very first thing that I talked about, tangent lines, right? So if I were to take this point right here and a second point and connect them together, then that line has 2 points, and we should be able to find the equation of it. Yes? Okay.
Yes.
Now, what if I were to tell you to take this point and slide it down and make it a little bit closer? So now your tangent line would look, your secant line would look like that, right? And that should have a slope also. And now what if I tell you to slide that point down even further, get it closer? Now you're gonna have a different secant line, right? And keep doing this. Slide that point closer. Now you have a difference. No, you don't. I just erased everything. Now you have a different secant line, right? Compare that to the original one. That was the original one, right? And as I've slid that second point, as I've moved it closer and closer to the first point, that secant line is started to tilt down. Now, what happens when I put that second point right on top of that red point?
You're getting it as close to no slope as possible.
Yeah, you're going for 0.
On top of it, though, I'm saying put it on top. So
Oh.
remember that if you have 2 points and you want to know the slope of a line between 2 points, it's always your rise over run, right? That's your rise over run is always your slope. M is rise over run.
So then there would be no, yeah.
All right, good. So let's go back to the original scenario. The original scenario, we definitely have a rise over run here, don't we?
Mhm.
Definitely.
Yep.
And as I move this point closer, every one of these points, I have some rise over run. But when I put the 2 points on top of one another, what's my rise?
None.
No, 0.
0. What's my run?
0,
Zero.
so it creates the
0.
hole.
So we have undefined, don't we?
Yep.
However, if I, instead of putting that point right there, right there, instead of putting it right on top of it, what if I put it really, really close to it? Would there be some rise?
Yes.
Would
Yes.
there be some run?
Yep.
Mm-hmm.
So what you're telling me is that right on top of one another, no go, right? But right near it, yes?
Mhm.
That's exactly what this picture is saying. At some point, we get undefined, but right near it, we have something meaningful. And that's exactly what this is all going to come down to, is this sort of problem, all right? So we'll get to, I hope that helps explain it a little bit, that the whole idea here is, and this is what, look, there were two people who developed calculus, Isaac Newton, and I believe his name is, last name is Leibniz. I always forget his first name. I should know. Leibniz and Newton. And their names will come up in our notes as we move on. What's amazing about them is that they both developed calculus. There was no calculus, okay? No one had ever thought of calculus before. They were the ones who figured it, like came up with it. They both did it at about the same time in history, and they did it independently without knowledge of one another. Although it's been debated that Leibniz actually kind of stole Newton's ideas. I don't know. It doesn't matter. Newton gets more credit. Everyone's heard of Newton, right? Because Newton's also got his laws of motion, and Leibniz is like, Leib who, you know? But what's funny is we use Leibniz notation. The notation that Leibniz used when he created calculus is the one that we like and we prefer. Newton's notation was a little bit, it was a little tough, but anyway, they were both struggling with this idea of 0 over 0. They're like, can we get around this idea? Like 0 over 0 is bad. We can't do anything with it, but there's got to be some. Look, these lines that we were looking at, each one of these lines is, if we were to draw like the sequence of lines that we're drawing, they're approaching something, like those lines, the slopes are approaching something, right? I mean, would you all agree that all of these lines, the slopes are positive? Right, because it's pitched up left to right. So they're all positive. This first one has a pretty steep slope. And as you keep moving, they get, you know, less steep, less steep, less steep. They're never going to be negative, right? Would you agree with that? They're not going to be negative.
Mhm.
So the slope is approaching something, right? And that's what Newton and Leibniz were saying. It's like, it's got to be approaching something. I know that I can never put the 2 points on top of one another because I get undefined, but in this sort of idea of approaching, it's going somewhere. Where? And that's what they were trying to figure out. Okay. Where am I? Notes. Okay. There's your function. New one, sine x over x. Now, I'm changing it here. Finally, we're changing. You know how we've been approaching 2, 2, 2, 2? That could have been any number. So now I want you to look at 0. What's happening to this function at 0? Let me see.
It's undefined.
Yeah,
Yep.
Next person up. Well, I'll get the next one. Marissa's going to be up, but that is going to be undefined because you get division by 0, right? You get division by 0 here, but just to make sure we all remember pre-cal, what is sine of 0? So f of 0 would be sine of 0 over 0, and sine of 0 is
1.
0.
1.
0, 1.
Isn't it 0? Because cosine of 0 is 1. So sine of 0.
So that
1.
It's 0.
It's
It's
0.
It's 0 over 0. Okay, so unit circle, everyone's got, you want to get to the point where you know all the values of sine and cosine on the common angles. And you don't want to have to go to your calculator for it. Okay, it's just going to slow you down, take more time. And if you're not there, it's okay, but you need to be there soon. Okay, sine of 0 is 0, cosine of 0 is 1, right? Sine of 0 is 0. So we get 0 over 0, this is undefined. So if we try to plug 0 into this function, it can't handle it. But do you think it can handle things near 0? I mean, if I plug in a number, as long as it's not 0, I should be able to take sine of it, and I should be able to divide by that number. As long as it's not 0, I should get an answer.
Yes.
Let's see what the picture looks like. So at 0, it's undefined, there's a hole, but if I don't look at that and look to the left and right, let's see, Marissa, you were up. Marissa, from the left, where's that function headed? Where does it look like it's headed? What's that?
To 1.
To 1, okay.
To
And then
1.
from the right, Marissa, what do you think?
To 1 as well.
1, right? So from both sides, it's headed to 1. So at 0, the function's undefined. But if you give me a value really, really close to 0 from either side of 0, doesn't matter which side, as long as you're close to 0, I promise you that the answer is 1. Are we saying it is 1? Or we're not saying it is 1, are we? We're saying it's close to 1.
Yes.
There's no
It's
value
close
of
to
1.
It's close. So close is a weird word, right?
Yeah.
Close is, one of the reasons that I enjoyed math when I was a student was that math was very black and white, correct, incorrect, right? You get the correct answer or the incorrect answer. And I realized later that math is not, that there's a lot of gray areas too, but initially I enjoyed math because there was no ambiguity to it. It wasn't left up to interpretation. Where like when I wrote an English paper, I would be like, well, this is just a great paper. It's the best paper I've ever written. And I get it back and I get a D, because they didn't like what I said. You know what I'm saying? Like math, things are either or correct or not correct. But when you start saying something like close, you start to open up this Pandora's box. Because what do we mean by close? We said that, I just asked Marissa, I said, as we approach 0, as we get closer to 0 from the left, we said that the function looks like it's headed towards getting closer to 1, right? But what do we mean by close? So I always like to give this analogy. Do you feel like we are close to one another right now? Like, do you think I'm pretty close to you right now? Not like emotionally. I'm saying physically, spatially, are we close?
You beat me to the joke. Nope.
No. Well, where do you live? Don't tell me exactly where you live. give me the area of town. Are you in San Antonio?
Actually, west myself.
West of San Antonio?
Yes, sir.
How far west? Hondo?
Outside of Castroville.
Castroville. Okay.
Oh,
Okay.
there
So
too.
who's closer than Cody?
I'm like
In Alamo
just
Ranch.
miles
Alamo
away
Ranch. I'm
from
in SeaWorld.
Castroville.
I'm
I'm
northern
here.
San Antonio.
Like to the
Okay.
college?
I'm across the street from Northwest Vista.
You are?
Yeah.
Yes. I'm 1604 Wiseman. I'm pretty close to the college too.
Yeah, Wiseman and Valley.
So is anybody out of state? No, everyone's here. Okay, so I would argue that Cody, you and I are very close to one another, almost right. I mean, just like next, like infinitesimally close to each other, relative to Alpha Centauri, which is the nearest star other than our sun, right? Or
Yep,
even
yep.
relative to the sun, we are all extremely close to one another, aren't we?
Relative to the moon. You can
Relative to the moon, right? So the problem with close, the problem with the word close is that it's all relative, right? It depends on,
context.
how big are we going here, right? I would say that you were extremely far away from me compared to my pen, right? My pen's right here, right? So close is relative. And so mathematically, we get into danger when we start using words like close. And in math, that doesn't float, right? We don't go that way. So there are precise definitions that we use to handle all this that we are not going to do in this class, right? There's precise mathematics. Are there any math majors in here? No math majors? Okay. So if you're a math major, I would tell you basically like you have to go take some other math classes and then you'll realize that we have to go back and do all the calculus over again with precise definitions. Here in this class, we're going to understand close to mean what you kind of think it is. Like 0.99347 is pretty close to 1. And we're not going to argue about it. All right, that's pretty close. Okay, this one here. And I feel like I already asked Marissa. So I think, is it Jair? Am I saying that right?
Jair.
Jair. Okay, so I actually say the J. Okay. All right, Jair.
Mhm.
What do you get if you plug 0 into this function? So what is sine of 1/0?
It would be undefined.
Undefined, right? I mean, you can't do the 1 divided by 0, right? You can't do it. So this is undefined. Okay, so this is undefined. But let's see what's happening near 0, because maybe if we go to the left a little bit or to the right, then we'll actually have something. You ready to see the picture? Comes. So this is the graph. This is a crazy graph. Let me try and zoom in. I'm going to zoom in. You can't even tell, but at 0, it's undefined. Okay, you can't plug 0 in. You can't even tell by looking at it. But let me zoom in. Let me try and zoom in. If you zoom in, you'll see that there's like all these squiggly things happening. And this is a crazy function because it wants to act like a sine function, but what's inside of it, as x gets close to 0, there's no easy way to explain this because we haven't talked about enough of this yet, but imagine that what this function is trying to do is as you get closer to 0, you start to have more and more oscillations. So you're starting to cram. You remember in pre-cal, you talk about the period of a function or a sine function?
2 pi.
It's, well, the period of the standard, if you do sine of, I think when you learn it, you learn bx plus c. Aren't you told that the period has something to do with this number in front of the x or something like that?
Yeah, it's
That's like
b
the
over 2
amplitude?
pi.
And then there's an amplitude is the number out front. So in this particular function, what's happening is this 1 over x inside is not like this. It doesn't look like this. So what's winding up happening is that as you try and get closer to 0, it tries to squeeze more and more periods in. And it becomes like infinitely many periods squeezed into a smaller and smaller space. And it just starts to oscillate craziness. I'll show you as we approach from the left what happens. Where are you here? Come on, there it is. So here it comes coming in, and let's just watch what happens here. It goes down and back up and down, back up. It just back and forth. And the closer you get to 0, the faster it goes. And so, whoa, sorry, I had it undefined there. Okay, so from the left, Jair, did you answer me? Yes, you did. You said it was undefined. So Matthew here.
Yes, sir.
Okay, so Matthew, from the left, as we approach 0, is the function headed to one particular value?
No.
No, it just like oscillates, doesn't it? It just goes nuts. So this is the first time this has happened, Matthew. From the left, our function is not headed to anything. And then from the right, Matthew, it's the same thing. Can you all see that? Can everyone see that from the picture? We have not had this happen. This is really just to illustrate that it can happen. That you can be undefined at a point, and from the left and right, it doesn't make any sense either, right? Okay, let me see here where we're at. I'm trying to see if I want to take my break right now. Take the break. Yeah, let's just do these last two and we'll take a quick break. Okay, so on this one, can you believe we're almost at the halfway point of the class? That's nuts. All right, so introduction. Look at this function. I want everyone to look at this function at 0. Okay, so if I asked you to plug 0 in, you would tell me
Undefined.
undefined. Okay, but what happens as we approach from the left? Take a look at what happens to the function as we try and get closer and closer to 0 from the left-hand side. Where is it headed?
Down.
Down where?
Towards,
Negative infinity?
yeah, I was gonna say negative
To
infinity.
negative infinity. The closer and closer we get to 0 from the left, the bigger the function gets, but negative. So in college algebra, we call that a vertical asymptote. The function is headed in and it's diving down, right? As it gets closer to 0, dives down. And then from the right-hand side, it does the opposite. As we come into 0 from the right, the function takes off, starts heading up to positive infinity. We have not had this happen before. At 0, it's undefined. From the left, it's not headed to a number, it's headed to negative infinity. And from the right, it's not headed to a number, it's headed to positive infinity. And remember, infinity is not a number, okay? It's an idea that something gets bigger and bigger and bigger. So you can't tell me like infinity minus 1 is not, that's not a fixed number. It's just still infinite. All right, last one, then we'll take our break. This function, 1 over x squared. At 0, it's undefined. From the left, where's it headed?
Infinity.
Positive infinity. From the right, where's it headed?
Positive
Positive infinity. Okay. All right, so we're going to take our break. I just want to recap. When it comes to this idea visually, we can look at what's happening at a point on the function. And in that case, we could have it spit out a number like 8 or 4 or something like that. It could be undefined, right? And then we can come in from the left and the right, and we can either have it head to a number, or we could have it oscillate and just not go to any number, or we could have it go to positive or negative infinity. And that could happen both from the left and the right. So there's a bunch of different scenarios that could happen here, right? So we'll take our break. And the next thing we're going to do is start to talk about this idea of using more like math language and notation. And then we'll do some more problems and hopefully move into the next section. So let's say it's 7:40, I mean 7:43, it's 2:43. We'll come back at 2:54. Okay, so 10 minutes. I'll put a little timer up here. And I am going to step away myself. So I'm not going to answer questions right now. If you have them, I can do that later. So 10-minute break. I'll be back.
Hey, Brian, are you there? Nope. Shoot again. Brian, are you there? Rip.
Okay. Let's get back to this. So now what we're going to do is just clarify some of the ideas here, and then we're going to start to introduce the notation that we're going to need to use to be able to, I guess, distinguish between algebra, stuff we've done in the past, and this new idea of kind of approaching a number from different sides. All right, so this is what I ended with just a second ago. You can read all this, but I'll just point out the big things here. When we are talking about the limit of a function at a point, x equals a, we're inspecting the behavior near that value. Okay, so anytime we talk about a limit, it's not what's happening at a, it's what's happening near a. When we approach from one of the sides of that value x equals a, we have three possibilities. The function can be approaching a number, okay? It can oscillate infinitely many times, and therefore it's not headed to a number, or it could approach infinity, positive or negative infinity. Those are the only three scenarios that you can have when you're approaching on a function from either the left or right hand sides. Now, with this idea, we now need to distinguish between what we call the left-hand and right-hand limits. So if we can approach a value from two sides, then naturally we want to call one, coming from one side, the left-hand limit, and the other side, the right-hand limit. So some notation that we're going to have, this is the first time that you're seeing this, is if I give you a function and I want you to investigate what's happening to that function as we approach a value from the left, here's what we will write. Lim, okay, we write lim, then x with an arrow pointed to, I'm going to write this a slightly different way. I'm going to write it like this. Lim. Underneath it, I'm going to put x with an arrow going to A. And then I'm going to put a little negative sign to the top right of the A. And that's what tells you it's a left-hand limit. And then f of x is the function I want you to investigate. So f of x is the actual function that you're supposed to figure out. And then if this is approaching something, then we will say the answer is L. L stands for limit. That's the limit of the function. So the negative here is the only thing that indicates to you that you're coming in from the left. And the way that I think about it is, your negative numbers are over here and your positive are over here. So if you're approaching, if the negative sign's there, you're coming in from the left side. And if it's a plus sign, then you'll approach it from the right. And that's the next definition down here, the next notation. Lim, x approaches A with a plus sign, f of x equals L. That's the right-hand limit. So that's purely just notation now. Questions on that notation? Now, what if I want you to investigate what's happening to a function at a value, but I want you to look both at the left and the right? You might think, oh, put a minus and a plus sign there, right? That way I look at both. Well, actually, we don't. What we do is we just write it without any symbols. So notice next to that A right there, I don't have a negative there and I don't have a plus. That means you have to look at both. So just be careful there. It's implied that you have to look from both directions. So just to recap, x with the arrow going to A like that means that we're letting x approach A. The lim, having a lim there written, just lets you know, hey, I'm not asking you, I'm not asking you this. I'm not asking you f of 2. That would mean college algebra, plug 2 in, right? Instead, using the lim lets you know, hey, look, we're going to be inspecting what's happening from a certain side. And then the f of x is the actual function that you're going to be investigating. So purely just notation here. Let's see this notation in action. So here's a graph of a function. Notice the x value here of 2, right? That's x is 2. And so look at this notation right here. Lim, x approaches 2 with a negative sign there, means I'm coming in from the left. Of this function, I'm saying that the answer is 8. Does everyone see why the answer is 8? As you come in from the left side, you come up and you approach 8, right? As you come in from the left, the function approaches 8. Caitlin, are you there, Caitlin?
Yes.
Okay, Caitlin, does it matter when I'm talking about a limit, does it actually matter that that is a solid dot there or not?
I would assume it would if there's
Yeah.
a solid dot instead of a hole.
So what if it was a hole? What I'm saying to you is if this was a hole, would that change that this answer is 8?
Yes.
Okay, so this is big. This is a big point for everyone here. When you're talking about a limit, you don't care what's happening at that point. Okay, so Caitlin, I don't care that at 2 I have a hole. I don't care. What I care about is what the function is doing as I get closer and closer to that hole, and it is still getting closer and closer to 8. Does that make sense?
Yes.
So in fact, I could have a hole there or not a hole. It doesn't matter. I'm almost like ignoring completely, just like not caring at all what's happening here. And just noticing that as I get closer, it gets closer and closer to 8. All right. Okay, now look at the one below this. The notation here, limit x is approaching 2 from which side? What does the plus symbol mean?
Right.
From the right, and I'm saying that the answer is 4. Do you all agree? Let's see, we're coming in from the right. We're approaching, here's 2, right? Here's 2 on the x-axis. As I approach 2 from the right, look at the y value. Look at this y value here. It's getting closer and closer to what?
4. But it's
4,
not
right.
going to equal
Closer
4.
and closer to 4. And see, do you see that I have that hole there? I don't care. I don't care that there's a hole. All I care about is that as I get closer, my y value is getting closer and closer to 4. Now this one, look at this. Limit x approaches 2. Do I have a plus or a minus up there? No, which means I have to come and look at it from both sides. So I'm saying the answer is 8. And the reason it's 8 is because as I approach 2, right? As I approach 2 from the left, it's headed towards 8, isn't it? And as I approach 2 from the right, it's also headed towards 8. And so from both sides, it's headed to 8. So I can put the answer as 8 because from both sides, it goes to the same place. Could I have said that with the previous example?
No.
Right? Could I have said that for this one here? You're correct. This would be incorrect to say the limit for this picture right here, to say the limit as x approaches 2 of this function is equal to 8 would be wrong, because not having the plus or minus here on the 2 means that you're going from both sides, and from both sides, this is not going to 8, only from the left side. Understand? So what we will say in this case, if someone were to ask you, what is this? You would say, well, from the left, it's 8, from the right, it's 4. So it's not going to the same place. So what I would say is that this limit does not exist. That's the language we would use. The limit does not exist here because from the left and the right, you get 2 different things. And we abbreviate that. You'll see me write this a lot instead of does not exist. I'll put DNE. That's a D, that's not a 1. I mean, that's not a 0. So does not exist would be the answer to that limit. Now the left-hand limit is 8 and the right-hand limit is 4, but the limit at 2 does not exist. Questions? Okay, let's see. So this is what I say here. We call the left and right-hand limits one-sided limits. That's what they're called. They only look at the limit from one direction. The limit as x approaches a without the plus or minus of a function, if we say it equals L, implies that we look from both directions and that we approach the same value. If that doesn't happen, then we say it does not exist. And there's that example right there. So this limit as x approaches 2 does not exist on this picture. How about this one? Look at this one here. Try and make it a little bit bigger.
You want to volunteer? Are you going to call on somebody or?
Well, let me first formulate my question. Here's 2, just in case you're unaware. That's x is 2. So my first question to whoever is, does the left-hand limit exist at 2? So as we come into 2 from the left, is it headed to a number?
Yes.
Yes. Now we did this problem earlier. Do y'all remember when we did this? It was headed towards negative 0.25.
Yes, sir.
For that one. Okay. So from the left, it's headed to negative 0.25. How about from the right? Does the right-hand limit exist?
It also works, yes.
Yeah, and it also is headed to negative 0.25, isn't it?
So would it be like limit of x plus 2 is
Limit as x approaches 2 of f of x.
it's equal to negative 0.25.
Exactly, that is equal to negative 0.25 because from the left and from the right, we're headed to the same value. It's very important that from the left and right, we're headed to the same place. And I'll point this out. What's happening at 2?
It's undefined.
Undefined. So the fact that it's undefined at 2, did that have any impact on the limit existing?
No.
No, because again, this is what calculus is about. It's that we don't care what's happening at 2. We're ignoring it. And we're seeing that from the left and from the right. In this case, we're headed to the same place. So the limit does exist there.
So, sir,
Yes.
so how it's written on the top, it's pretty much like a broken down version of what we just wrote.
I'm not sure I'm following your question.
Like a simplified version of the limit x goes to 2.
I think he's asking about the right below the blue.
These?
Mm-hmm.
Yeah, this is just showing you that the left-hand limit is equal to the right-hand limit. And because the left and right-hand limits are equal to one another, that means that the limit, right, without a plus or minus here, the limit is also equal to negative point. That should be negative 0.25, not 0.25. That's a typo. I don't think I've ever noticed that typo in this. Let me open up my code here. For those of you who are computer science majors, math.
I was about to say, you code all this?
Yeah, say hello.
Yeah, I code all this. It's not as impressive as it looks. Mathematica is a very, very user-friendly language. It's C++ with a ton of built-in functions. So I just call on built-in functions all the time. I mean, you do have to have proper syntax, but I've been using this program. They're on version like, I think 12 or 13. And I've been using it since it was 1.4. So like when I was a student, I was using this. So I've got, the syntax is not a problem for me.
I had a, it's kind of, since you brought it up just real quick, do you know what discrete mathematics is? Because I know I have to take it for my computer science, and I believe it's something that links the mathematics to the programming itself, but I'm not sure.
Discrete mathematics is like this, cornucopia of math topics. It's a bunch of stuff. It's not something that I can just say, oh, it's this, like algebra is manipulation of equations and expressions. That's a conversation we can have in maybe in office hours. We can go look at like topics and stuff. It's a lot. Students struggle with that class. I'm not sure why, but they do. Maybe it's because it's so many different things, but. Okay, all right, so now the definition of the limit, just, so we have a definition. Suppose f of x is a function that is defined not at a, but near a. Then we will write limit x approaches a of f of x equals L. And we will say the limit as x approached a of f of x equals L. So that's the way you say that. The limit as x approach, you know what that should say, approaches a of f of x equals L. And this is where I do a little bit of hand waving because, again, a pure mathematician, this is not the definition of the limit. For a pure mathematician, it's a much different definition. And nobody here is in a math major that no one said they were. So I'm just going to we're not even going to go down that road. Okay. But just be aware, there is a precise mathematical definition of the limit, and this is not what it is. For us, we're going to be happy to just say arbitrarily close, and nobody asks about what do you mean by close. All right. Okay, all right. So now we're gonna do an example. This is the last example of the section. We really haven't done much work. We've just been looking at things. This is the first example that we're gonna do where what we're going to do is we're going to put all of these concepts together. And I'm going to give you a bunch of properties of a function. And I'm going to ask you to draw me a function that has these properties. So it's kind of like we're going to go backwards. Okay, so here we go. I'll say this to start the problem. Everybody's picture is going to be a little bit different. Everyone's going to have a slightly different picture, but we all need to have properties 1 through 8 be true. So let's just take a look at the properties before we draw anything. The first property that this function we draw has to have is that as we approach x, as x approaches -2, notice that that's -2. That is not 2 with the little negative to the top, right? This is as we approach -2, the function, the limit of this function has to be 3. What that would mean is that on our number line at -2, our graph must be coming into, from the left and the right, it has to be approaching 3. So I'm going to try and draw that. Let me change my paper here. I'm going to have to be scrolling back up and down to make this work. So if I go to -2 on the number line, what I know is that as I approach that value, right, because it's a limit, as I approach that value from both sides, right, because there's not a plus and minus, from both sides, I have to be headed towards 3, a y value of 3. So I'm going to go here and graph 3, 1, 2, here's 3. So here's what I know. Watch the way I draw this. I'm going to put an open circle here, and then from the left, I'm going to make it do this, and from the right, I'm going to make it do that. That's all I'm going to draw right now, just that little piece. Do you all agree? Or maybe I should ask Nathan. Nathan?
Yes.
Nathan, do you agree that property 1 is satisfied with that picture? That as, let me make this a little smaller.
I would say no because it's, oh wait, property 1.
Yeah, is property 1 satisfied with this picture? If I were to tell you to look at that, as you
No.
approach -2, from the left and the right, are both sides approaching a y value of 3?
They're approaching it, but they don't equal 3.
That's right. Okay, but that's what the limit's about. The limit says you're approaching 3. You don't ever actually have to get there, Nathan. You just have to be approaching it. Okay, so are you approaching 3?
Yes.
You look like you're not happy with the idea of approaching.
I don't like it.
Yeah, it's weird. It's a little weird. You just have to get arbitrarily close. I mean, and don't get too upset about it, because all we're saying is that, I don't know how to do this without getting into the precise definition. I'm going to have to.
I think
So-
the easiest way is just to look at it as asymptotic. You're never going to get there. So just look at what's happening on both sides. You're not going to have the approaching in that sense, but just the general idea of you can't get to 3 here. Just think of it that way.
You don't have to get to 3 for the limit to exist. You don't have to. You could get to 3, but you don't need to for the limit to exist. Let me try and do it this way. Nathan, I realize that I'm never going to get to 3. Okay, I realize that. But I'm saying to you, Nathan, that I can get close to 3. So Nathan's like the ultimate skeptic here. So Nathan says, I don't believe that you get as close to 3 as you think. So I ask Nathan, how close do you want me to get? So Nathan, how close would you like me to get to 3?
2.999999999.
Okay, 2.999. How many 9s do you want?
3 is good.
3?
Yeah.
I'll do you better. I'll go out 6, okay? So Nathan thinks that I can't ever get that close to 3. So all I have to do now is figure out a number down here, okay, that when I plug it into the function, I get a number that's a little bit bigger than this. Okay, so 2.999 with 7 9s instead of 6. And what I'm saying is that because this hole, think about the hole. How wide is that hole? This is kind of a weird idea, but how wide is that hole?
It's
Alejandro,
only
you-
at 3. It's
What does
Just
that
like
mean,
a quick
Alejandro?
one?
How wide is a point?
just the one point itself, like that
Like if I
exact.
draw a point, if I draw a point on the number line, how wide is a point?
It's
Just
just
that
that
one
number, right?
In
Yeah.
unit.
The
So,
exact unit.
Yeah.
here's the number. Let's say that's the number 1 on the number line. How wide is that point? It has
It
no
only
width.
stands for that. Yeah, it just doesn't
It
it
has
just
no
stand?
width. A point has no width. Now, physically, if I draw it with a pencil, of course it has width, but I don't want to say theoretically because I don't want you to not think it's real, but the number 1 on the number line, that point on the number line has no width. In order to have width, you have to have a segment. Then you have width. So this hole, even though I'm drawing it, that hole has no width to it. It's just at one point that there's no point. And this is a weird concept. I can tell just by the look on your faces.
No,
I mean, I get it.
I think
It's-
I understand that now.
Like it's
Okay,
theoretical,
so-
it's a
Yeah.
spot in space that we have to imagine as like a location, not any kind of actual measurable.
Yeah,
Kinda thing.
if it has width, then it's no longer a point. It would be either a disc, right? When you draw a dot, that's actually a disc if you zoom in on it. Right, so theoretically, a point on a number line has 0 width. Just like if you draw a line, right? If I draw a line, that has a length, but it doesn't have an area. A line segment has no area to it because it has no width. A line has no thickness to it, in theory. Okay, we're going off here now. Okay, so let me get all this crap out of here. Okay, so Nathan, are we okay to say the first condition satisfied?
Yes.
Okay, all right, how about the second condition? This is this a calculus condition or not?
That's algebra.
That's algebra. It just says that when we plug -2 into the function needs to spit out 0, which means that when I draw this at -2, I need to have a point right here. That's why I left that open. That's why I did not fill that in earlier, is because I didn't know, the limit doesn't tell me what's happening at -2. It only tells me what happens near -2. So that's why I left it open. And I'm glad I did, because at -2, we're actually down here at 0. The third condition, I'm going to call on someone. I don't know how this is going to work, but I'm going to see if Brandon can help me draw condition 3. Are you there, Brandon?
Oh yeah. My voice might be raspy, but I'm here.
So what do you want me to do to satisfy condition 3?
Okay, so it has to come from the left-hand side.
Of 1, right? So how about I put 1 here on the number line? Like 1 is probably about right there.
And sir, are these all in the same graph?
Yep,
Oh, so we're not doing multiple, okay, one big graph.
it's all one graph. that
Oh,
has to
it's one big
satisfy
graph.
all of these at the same time.
That is something.
So you said this right. We're going to be approaching 1 from the left. And what y value is this function approaching?
-1.
-1. So let me do -1 on my y-axis. Here's -1. And then I need to, from which side you said, Brandon?
From the left.
Left. So from the left, I need to be approaching -1.
Yes.
So I could have come in from there, or I could have come in from the bottom. It doesn't matter. And at 1, can I put is it okay with you if I put an open circle there? Because I don't care what's happening at 1.
So sir, when we put an open circle, is that the safest bet so it doesn't interfere with any other of the...
That's just to let you know, that gives you, I guess, guidance as to what I'm approaching, and letting you know, the open hole lets you know that I'm not saying it's defined at 1 to be anything. This condition 3 tells me nothing about what's happening at 1. Okay, I have no idea what's happening at 1 with just condition 3. I know what's happening near 1 as I come in from the left. That's all I know. So that's why I left it as a whole. So just so you know, I'm not trying to claim that anything's happening at 1. That makes sense,
Okay.
everyone?
So you're saying that just we have ideas when they give you the limit, you just have idea of directly to the left or the right, depending on what they give you?
That's right.
Okay. So that's
Yeah.
why we're not actually creating like real function. We just have these little segments. Okay.
So it's
Yeah.
not, is it hypothetical or is it just?
Well, we are drawing a function. See, somebody else, okay, this is why I said everyone's graph could look different. Someone else could have made that first condition look like the blue one there. And that still would have been the limit from the left and right are both headed to 3. It's just their picture looks a little different than mine, right? And someone down here on this one could have had their graph come in from there, like this. And it's still approaching -1 as you come in from the left. So everyone's picture might look slightly different. Cody, you're next on the list here. So do you want to help me draw condition 4?
Sure thing. So we're coming from the right. And it says, as we approach 1, we should get the value, a y value of 2
Okay.
as we
So
come from the right.
What do you want me to draw?
So I want a dot from, I want an x value of 1. And then I want it, as it gets closer to 1, it approaches 2, or it gets to 2.
Okay, so how about at 1, 2, I draw an open circle like that.
Yep,
At
that'll
1,
work.
2, and then from the right, just draw a little squiggly out the right side.
That'll
Like that?
work.
That works, right? That means from the right-hand side, the function is approaching 2.
Mhm.
Okay, we've got the first 4 conditions. All right, Samuel, you're up.
Yes.
Okay, Samuel, what about the 5th condition? Is that algebra or calculus?
Algebra.
Okay, and it just means that when you plug 1 in, you get what?
2.
Okay, so what do you want me to draw?
So would it be the y equals 1?
If this is your x, right? If your x is 1, your y is 2, right? So I just go x is 1, y is 2.
So it'd
and
be a
that should
solid
be
dot.
Okay, that should be a solid dot. So I now see I left it open because I wasn't sure what was going to happen there, but it just so happens that the 5th condition is telling me to fill that in with a dot.
So will that affect the condition before?
Nope, because the condition before, the limit from the right, did not care what's happening at 1, right? It doesn't care what's happening at 1. It only cares about what's happening as we get near 1 from the right.
So we could see it as a shaded circle
Mhm.
being circled by a circle.
Yeah.
That sounds weird to say, but yeah.
Good
Okay,
target
next
almost.
condition, Christian. Christian?
So for 6,
Yeah, 6. Can you see it?
yeah. So
Okay.
it would be coming from the left to x of 4.
Okay, so let me get x is 4 on my graph. Okay, so here's x of 4. And as we come into the left-hand side, what do you want me to do?
It goes to positive infinity, so it just goes like straight up.
Let's go straight up. And in college algebra, we call these vertical asymptotes, right? So it's almost like we have a vertical asymptote like this. Y'all see that? As we approach condition 6, as we approach 4 from the left, the function needs to go to infinity. So as we approach 4 from the left, it needs to go up. And it keeps going here, vertical asymptote. Good, Christian. All right, Naja, am I saying that right? Naja?
Yes, you're saying it right.
Okay, how about the 6th condition, 7th condition, sorry.
As it approaches 4 from the right, it approaches 0.
That's weird. Okay, so what should I draw? As we come in from the right, the function needs to head to where?
0.
0. So that's the x-axis, isn't it?
Mm-hmm.
So at 4, 0, I'm going to draw an open circle, right? Now, I don't want to put a dot there because the limit tells me nothing about what's happening at 4. And then I just need to come in, you know, from the right, however I want. If you want to come in from here, you could. It doesn't matter. As long as you come in from the right, headed towards 0. Good. I'll let you do the last one, Naja, because I think the last one, there's not much to do, right? What
Yeah,
does it say is happening at 4?
it's undefined.
Fine. So I'm just going to leave this kind of vertical asymptote here. I'm going to leave that hole there. I'm never going to fill in anything. Okay, we have drawn something that satisfies all of the conditions. Now, we're not done, okay? Because now what I'd like to do is actually make this look like a function. And remember, all functions have to pass the vertical line test. So what I can do now is go back to kindergarten and I can connect pieces together, like almost like connect the dots. So I'm going to start here with this point we had here and to the left. I'm just going to draw whatever I want. I'm going to just make it go out to the left like that. And then here, this little piece, I'm going to connect it to this piece, however I want. And then here, I'm going to connect these two together. And then out the right side, I'm going to make it go up. And then, I don't know, I'm just going to have fun and bring it back down. There we go. I have now drawn a function. Function meaning it passes the vertical line test. And that function that I drew satisfies all 8 conditions.
It's like so limits are almost like a guide to a super piecewise function almost.
Yeah, in this particular case. And like I said, everyone's would look a little different, right?
True. Yep.
I mean, you could actually have somebody draw the same conditions and theirs could look like this.
So why did you leave -2, 0 out that point?
Where? This-
The
wait.
solid, yeah.
It's there. Why did I leave it out? What do you mean out?
Like you didn't. Oh,
I
I'm
didn't-
sorry. You didn't connect it, yeah.
Well, because you can't. It's
Is it just a like product of that?
it's just a property of this function. It's just
Yeah.
that everything's connected together here. The limit exists, but then at -2, it's down here.
Okay.
It's just the way the function is. So in green, I'm drawing in green now. Somebody else could have done the picture in green. And that picture in green would also be correct because every condition is the same. All 8 conditions are met. So, you know, these problems you have to, you know, play with it, but I think this is these problems are good for you, like demonstrating that you understand what these notations mean, right? All right, we're moving on, unless there's a question. All right, so everything we've done has been visual, right? Whether it be when we first started and I was having you look at graphs and say, hey, coming from the left or right, I provided you the picture, right? Or in this last problem we did, I provided you the conditions and we drew a picture. Now what we're going to do is we're going to talk about limits with no pictures. Okay, so now we want to be able to figure out the limit of a function without anybody showing us a picture at all. Okay, so this is where things start getting difficult. All right, so here we go. Before we can start doing this, I have to establish what are called the limit laws. And these are the things, these are truths, okay? These are things that I'm telling you you're allowed to do when you're looking at a limit of a function. Let me check something. I think I had something in the chat here.
Oh, no question about the chat. Are we only allowed to direct message you?
I don't know. Do I have that set up that way right now?
I think so, yeah.
I can open it publicly. Yeah, there we go. I think my default setting is just me, which I'll do during the tests. but for lectures, it's okay to have it open. Just remind me if I forget about it. Okay. Okay, so the limit laws, I'm just going to run through them real quick, and then you'll see as we do problems how these laws work. The first limit law says if you have two functions being added together and you want to find the limit, that you can look at the limits of each function individually. So it allows you to break it up into two limits. And the same goes with subtraction. If you have two functions being subtracted and you want to find the limit, you can look at them individually and then subtract the answers. Don't worry about writing all these down. I'll refer back to these. This third one says that if we have a constant in front of a function and we want to know the limit, we can just bring the constant out front and take the limit of the function by itself. I will show you that again once we get examples. This one says that if we have a limit and we have a product inside, two functions being multiplied together, that we can take the limit of each function individually and multiply those two answers together. Same goes for a quotient. If we have division, we can do the limit on the top and bottom separately and then get an answer. Yeah, let me see here. These I'll come back to. I want to get to these I'll go, as we do them, I'll cover them. I want to get to this thing called the direct substitution property. This is probably the most important thing to know going in to what we're about to do. All right, so when we talk about functions back in college algebra, we had this idea of something called the implied domain. Okay, so if I were to give you this function right here, f of x equals square root of x over x minus 4. There are certain numbers you cannot plug into this function. One number you can't plug in is 4, right? You all agree because you get division by 0? Mm-hmm. And you can't plug any negative numbers in, because if you try and do a negative underneath a root, you're going to get imaginary numbers, right? And we're not allowed to play with imaginary numbers in this class, okay? In fact, you're not allowed to play with imaginary numbers in any calculus class that you take, Cal 1, 2, or 3. We don't touch imaginary numbers. Those come later, all right? So just keep that in mind. Square roots of negative numbers will never be something we can work on until after Cal 3. So we can't plug negatives in here. So the domain of this, the way we write this, is that the only x's that make sense in here are x's that are real numbers. That's what that symbol means. So x is an element of the real numbers such that, that's what the colon means, x has to be greater than or equal to 0. Okay, so we can't have negatives in here, and x can't be 4. This is known as the implied domain. It's the values of x for which the function is defined. So even though someone may not give you the domain, it's implied from the definition, the way it's written out, and you should be able to determine what the domain is. So now the direct substitution property. This is the big daddy right here for right now. If you're looking at a function f, if it's a polynomial function, that's college algebra. A rational function, that's college algebra. A trig function, that's pre-cal. Exponential function, that's college algebra. Or a logarithmic function, that's college algebra. Basically every function you've studied in your life. If it's one of those, then if you want to take the limit of that function at some value a, so figure out what's happening as x approaches a, the answer is always just going to be plugging that number into the function. That's what the answer will be. As long as the a is in the implied domain. Now, what the hell do I mean? So let me just show you real quick. Let's say I give you this function. And I would like to know what is the limit as x approaches 3 of that function. Okay, what if that's the question I'm asking you? Right? Well, the function that we're looking at is x squared plus 2x plus 1. That's a polynomial function from college algebra. Are there any domain restrictions on this function? Is there anything you cannot plug in?
No.
No, you can plug any number you want in there, right? So 3 is definitely in the domain, isn't it, of that function?
Yes.
So this direct substitution property says that my answer to this is just plugging 3 into the function. So just plug 3 into that, you get 9 plus 6 plus 1 is 16. So your answer should be 16. Which means that if I graph this function, if I were to graph this, and I go out to 3, what I can tell you is that the function will be approaching from the left and right, it should be approaching 16. And at 3, it will actually be 16 because it's 3 is in the domain. So all the direct substitution property does is allows you to not have to deal with complicated stuff as long as the function is a function you've studied in your life, and as long as the thing you're trying to plug in is in the domain. If that's the case, just plug the number in and you're done. I'll give you one more example. Let's say I want to know the limit as x approaches 2 of x plus 3 over x plus 2. So this thing right here is the function we're talking about. So you look at this, are there any problems with this function in terms of a domain? Is there anything you cannot plug in?
Yeah, you can't have a negative 2.
Negative
Can't
2.
have negative 2, right? Now, am I approaching negative 2?
No.
No, I'm approaching 2, right? So this is no problem. I should just be able to plug 2 into this, 2 plus 3 over 2 plus 2. My answer is 5 over 4. So 5/4. Now let me show you visually what we're doing. If I take that function, x plus 3 over x plus 2, and what were we approaching? 2, right?
Yeah, we were approaching 2.
If I go to 2 here, here's 2 on my graph. If I go to 2, and I go up to the function, I should be approaching from the left and to the right. I should be approaching 5/4. 5/4 is 1.25, isn't it? 1.25, something like that. Let's see where we are. Right around here, 1.25. You see that to the left and to the right? Real close to 1.25. So again, if you're trying to do a limit and the number that you're plugging in does not cause any problems with the function, then you just plug the number in and the answer is the answer. And you're done. There's no work to be done. So this is nice, but this is not what you're going to be doing. I'm just trying to point out, like, when this happens, let's not waste time. Let's just plug in numbers and we're done. Let's look at something that's more in line with what we're going to have to deal with, which is something like this. So this is your first limit where things are going to go bad. And then we're going to learn how do we deal with them. All right. So limit x approaches. Let's go to 2. And let's do x squared minus 4 over x minus 2. Right. So the first thing that we want to do, Daniela, you're up. How are you doing, Daniela?
Good, thank you.
Hey, can you make my office hours by chance sometime this week or not?
Yeah,
Okay, try and visit with me. I'd like to talk to you.
okay.
Okay. So Daniela, whenever we have a limit like this, first thing we want to do is try direct substitution. Just see what happens if you plug 2 in. All right. In this case, 2. So Daniela, what happens if I take 2 and I just plug it in? What would I get?
I will get 4 minus 4 and then 2 minus 2, and that will be equal to 0 over 0.
0 over 0, right? So good, Daniela, thank you. So this is now a problem, all right? This is the problem that Newton was running into in Leibniz. It's like, okay, what's happening here, right? At 2, we're undefined. We're undefined, right? So, but we're trying to figure out the limit. We're trying to figure out what's happening near 2. So let me show you this graph.
I kind of wanted to jump ahead possibly, but I'll wait, never mind.
So here's the actual graph of that function. This is x squared minus 4 over x minus 2. And I want everyone to see what's happening at 2. Now you can't see it because this computer is not showing it, but there is a hole here.
Yeah,
We know there's a hole because it's undefined. Don't we know that?
Mm-hmm.
But does the left and right hand limit exist?
Yes.
Are they headed to the same place?
Yes.
From the left and right? Yes. What does it look like it's headed towards?
4.
Looks like it's headed towards 4, right?
Mhm.
But how are we going to figure that out without the graph? Right? That's what the question is. Like, okay, we know that we get 0 over 0. We know that that's a bad thing that's happening, but how are we going to be able to get to the answer 4? So that's the question. Everyone got that? I'm going to show you how, but a couple of things I want to point out before I get to it. From here on out, everyone, anytime we see this, when we're taking a limit, anytime we see this, we are going to think to ourselves that this is bad, right, Daniela? This is bad. 0 over 0 is bad. And anytime we see 0 over 0, we're also going to be thinking to ourselves, we need to do some algebra, or we're going to need a trick. So from here on out, when you are taking a limit, and the key here is that we're trying to limit, right? We're not trying to, I'm not telling you to plug 2 into this function, tell me the answer, because that would be undefined. But because this is a limit, we're trying to figure out what's happening near 2. When we get 0 over 0, we have to say, oh, this is bad. I need to do something now. Okay, I need to do something. So you ready for the work now? Here's what I'm gonna do. I'm gonna realize that the numerator is a difference of squares, right? X squared minus 4 is the same as x plus 2 times x minus 2. And that's all over x minus 2. And now I can see that the x minus 2 factors cancel. And once the x minus 2 factors cancel, I can now ask myself this question. What's the limit as x approaches 2 of whatever was left, which was just the x plus 2? And now try direct substitution. Think about this in blue as being like the new function. You don't have any problems plugging 2 into that, right? So if I just direct substitute 2 into here, I get 2 plus 2, and that is 4. And that's exactly what the picture showed us should be happening, right? Make sense? So we took a limit, we got 0 over 0. That told us there's a bad situation. We need to do some algebra, some trick. In this particular case, we did a difference of squares and everything worked out perfectly, right? Okay. Now, let's try another one. Would you all agree with me that x squared minus 4 factoring into x plus 2, x minus 2, that's like baby math? I hope that you look at that as being like baby math right there. Like
Yeah, it was.
Squares, that shouldn't be a big deal. Let's try something a little harder. Limit x approaches. Let's go with -3, because we haven't done a negative. Let's see, x squared minus x minus 6 over x squared minus, no, plus 3x. Hold on a second, hold on. You did something wrong here. There, let's try that. X squared plus x minus 6 over x squared plus 3x. So I would like to know, if you were to graph this, what's happening near -3? So first thing that we're going to try, Alejandro, are you there?
I'm here.
Okay. First thing we're going to try, Alejandro, is just replacing all the x's with -3. Okay, that's called direct substitution. So let's try that first. Okay, Alejandro? I'm going to do that kind of with an arrow, and I'm going to just do it in red. Replace all the x's with -3. Alejandro, I'll give you a minute to look at that and tell me what you get on top and what you get on bottom.
On top, I get 0, and on bottom, I also get 0.
Okay, good. Everyone got that? We get 0 over 0. Now you have to check that, okay? Because Alejandro, if you got like, what if you got 0 over 4? Okay, just hypothetically, Alejandro, if you got 0 over 4, that would just be 0, wouldn't it? But
Yes,
0
sir.
divided by 4 is 0. Or if you got like 2 over 4, then that would just be 1/2 and you'd be done. The only thing that's going to be interesting to us is when we get something bad, which is this, which is bad, which means we need algebra or trick. Look, forewarning to everyone, if on a test you do these problems and you put 0 over 0 and you box it and you say that's your answer, that means you're going to get no credit. Because this class is all about what do you do when you get 0 over 0? Like how do we get around it? So Alejandro, algebra time. I think probably for now, okay, the biggest thing that we have for us algebraically is factoring. So Alejandro, do you recognize that the numerator and denominator both factor?
Yes, sir.
Okay, so let's see. And this is where everyone's factoring is going to be at a different place. So Alejandro, not to put you on the spot, but how do you feel about factoring that numerator?
Actually, I think I've got the answer for that already.
Okay. All right. So did you factor it yet?
Yes, sir.
Okay, what did you get for the top factored?
It's going to be x plus 3 and x minus 2.
Okay, good. And then the bottom, can you factor that?
Oh, yeah, that's real simple. You just got to take out the x, and then you'll just get x and in parentheses x plus 3.
Yep. Okay, so on the top, it was just you're factoring a trinomial, which goes back to your college algebra days. And then the bottom is just GCF, right? Greatest common factor, pull an x out of both. And fortunately for us, we get a factor to cancel. And now you're ready to run the limit again, right, Alejandro? You're going to run this limit again. You're going to let x approach -3. But now your new expression just has an x minus 2 on top and then an x on the bottom because everything else canceled. And now direct substitution, what do you get, Alejandro?
Well, you would plug in the -3 on top, which will give you -5. And then the bottom would just be -3. And since they're both negatives, you can just, I guess, simplify that to 5 over 3.
There you go. The answer is 5/3. So if we graph this, right, if we go and graph this function and we look near -3, we should see that the function should be approaching 5/3. Should we see it? I mean, I guess it won't hurt to take a look. X squared plus x minus 6 over x squared plus 3x. Right, that was it, right? So I go to -3, which is right here. There's -3, and if I go up to the graph, at -3, there's a hole, right? There's a hole there. The computer's not showing it to me, but there's a hole. But from the left and the right, we have the value looks to be getting closer to about 1.66, maybe 1.67, somewhere around there, which is about 5/3. Okay, and that would be from the left and the right. But we didn't need the picture to do that. We could do that just with algebra. Okay, so far, all you've needed to be able to do this is just some level of factoring skill, right? Just some level of factoring skill. Let's do another one. Jesse, you're up, and I'll give you a moment to write this down. But Jesse is going to tell us what is happening when we try direct substitution. I'm sorry, Jesse, I think you're talking and you're muted.
That's my bad.
No, it's
What I
okay.
said,
It looked like you had a lot to say though, so.
no, yeah, what I said was it would be 0/0 as well because you put the 9 in the square root, which would be 3. So 3 minus 3 equals 0. And then on the bottom, it would also be 9 minus 9, which would equal 0.
Okay, so Jesse, when we see 0/0, we realize now that we're gonna need some algebra, right? This is bad. Okay. Now, look, unless you've seen calculus before, which some of you have seen calculus before, for everyone else, the next step is not going to be immediately clear. This is one of those things where if you've never seen this before, you need someone to show it to you, so then you kind of know what to do from here. All right. So how about factoring? Is there any factoring that you can do? Do you see anything from college algebra factoring wise?
No, I mean, my guess would be to square it to clear the square root, and then you could have a difference of squares on the bottom.
Yeah.
Okay, so when you said square it, what do you mean?
Like apply a square to the entire thing, so it would then turn into x minus 9 over x squared minus 81, and then you could turn that into a difference of squares and then possibly reduce further. It's my guess.
Okay, no, this is good because normally when people see square roots, they want to square the square root to make the square root go away. I think that's a very natural instinct. But let's think about this. Can we do that? Right? So in the past, when have you ever been allowed to square something?
Wouldn't
Guess
that
it-
like change it though?
Yeah, it would change the limit, I guess.
Yeah, so in the past, anytime you've ever squared things, because I know you have in algebra, you're allowed to square things, but it had to be an equation and you had to square both sides, right?
Right, you had to.
This is an expression, and when you square an expression, you change it. Just like this. If I write x equals 3, okay, let's just think about this. If you square both sides, and then go back and get x by taking the square root on both sides, you have to take the square root and go plus or minus, you'll get x is equal to plus or minus 3. So back in algebra, this is a reminder, when you're in algebra, when you start with an equation, you're always free to square both sides because it doesn't change your answers. What it does is it introduces possibly what are called extraneous solutions. So you might have to go check your answers, but it doesn't jeopardize your ability to solve the problem. You just have to be careful with it. But if I give you just 3, not x equals 3, but if I just tell you, hey, everyone, 3, and then you just go square it, now it's 9. 3 and 9 aren't the same thing, right? So we cannot just arbitrarily square things. Okay, we can't. Now, another thing though, let's just say we did, okay? Let's say I took this expression, and let's just say, for the sake of like just argument here, let's say I did allow you to just square this right now. If you squared it, this would actually become this times itself, right? And that means you would have to do a foiling out of the numerator and denominator. And this would become very complicated because you would have this times this is x, this times this is negative 3 root x, this times this is negative 3 root x, this times this is positive 9. And then all of that would be over this times this, which is x squared. This times this, negative 9x. This times this, negative 9x. This times this is 81. And so your final expression here would be x minus 6 root x plus 9 over x squared minus 18x plus 81. So even if we could square it, proper squaring of it gives us something pretty freaking nasty, if you ask me. It's
Yeah.
not as simple as just squaring each term. We have to be careful, right?
Mm-hmm.
Okay, so let's back it all the way up. We're at 0 over 0. Things are bad. We need some way of figuring this out. So now it's time to show you something. Maybe somebody who's seen this or knows how to do it can help us.
You could multiply by the conjugate, which would be the square root, which would be like the square root minus x times the square root plus 3.
Okay, Jair, right? That's your name, Jair?
Yes.
What the hell are you doing, Jair? Where are you coming up with that from, right? Does that not seem weird, everyone? Just to like all of a sudden multiply by the conjugate on top and bottom? Now, it's gonna work, but how did you know to do that, right? You've seen that, right? Someone has shown you this, or you know conjugates can help us out with expressions, right?
Mhm.
So I just want everyone to know that's not a natural move right there. Okay, that's not something you just be like, oh, let's do it. This is something you've now seen, and now you know this is fair game. This is on the table. And normally you want to use this when you see square roots. You want to be thinking conjugates. Now the conjugate is this same expression, just with a plus in between. Now, amazingly, things are going to work out. Why did I have to do it on the top and bottom?
So you
What
don't
happened?
change the value.
That's right, because everything in blue here is 1, right? And anything times 1 is itself. So even though we're going to make this thing look different, it's not going to be different. It's the same expression because I multiplied by 1. This is weird, okay? If this is your first time seeing this, this should be like, okay. Okay, limit x approaches 9. Now let's do the top. When I multiply the top out, things actually are really good. Because when I do root x times root x, what do I get?
X.
Just x. What about the middle terms? I'm talking about this one in green and that one in green. What will happen to those two?
They cancel out.
Yeah.
Cancel out, right? That's the whole idea behind the conjugate, is that the middle terms will always cancel. One of them is positive 3 root x. I'll put it down here just to have it. First one's positive root 3x. The other one is negative 3 root x. And now your final multiplication, negative 3 times positive 3 is negative 9. And then all of that is going to be over. Now, let me point something out here. Do not multiply out the bottom. Don't. Just leave it as x minus 9. I know you're like, why not then? We did the top. I'll show you why. Just leave the bottom alone. X minus 9 in parentheses times this.
You can
Do y'all
drop
see
your,
why I'm leaving it alone?
yeah, you can factor out your x minus 9s because the other stuff cancels.
This stuff cancels, and so you're left with limit x approaches 9. On top, I have x minus 9. On the bottom, x minus 9 in parentheses, square root of x plus 3. And now these two factors will cancel. The x minus 9s are factors, so they will cancel. I'll be left with limit x approaches 9. Now be kind of careful here. When you cancel that x minus 9 on top, you actually were left with a 1 up there. And on the bottom, you're left with the square root of x plus 3. And now, if you let x go to 9, you no longer have 0 over 0. You have 1 over the square root of 9 plus 3, which is 1 over 3 plus 3, which is 1 over 6.
I'm just upset. I should have known to use conjugate when you see the square root. I forgot about that.
Yep. So, you know, when I said if you get 0 over 0, that's bad, be thinking algebra or some trick, right? this conjugate is, at the end of the day, it is algebra, but it's kind of a trick, isn't it? It's kind of like, hey, check out what we can do, you know, like it's not very natural.
Yeah, it's kind of janky manipulation, but it works.
Yep. All right. Still doing all right? We only have 30 more minutes left. I guess think about it this way. We're only going to do this 16 times that we're going to meet. So maybe that makes you feel a little better.
I'm trying to figure out who's crazier, us for signing up for the class or you for volunteering to teach it.
Yeah.
Oof.
I love teaching the summer calculus stuff, but I usually like to do it face to face. But hey, it is what it is. Let's go something other than 3. Let's go to 5. Okay, I'm going to let you look at this for a few minutes. And I've gone through everyone. Is there anyone I have not called? I don't want to see if I've got everyone on my roster here. Anybody I didn't call? I went alphabetically today, with the exception of Jesse, who I put here at the bottom. From here on out, I will have my computer randomly shuffle you every day, and you'll just, whatever the computer, wherever you come up is where you come up. All right. Okay, so I'm going to let everyone look at this for a minute, see what happens. I'll check in with you in just, let's say, a minute and a half. Okay, sorry, that was a little longer than a minute and a half. All right, so I'm not sure how I want to do this. We'll do it this way.
Well, for the numerator, that equation, wouldn't you just be able to multiply 1 over x squared by 25 over 25, and then the 1 over 25 by x squared over x squared?
Yeah, so when you first try the direct substitution, is everybody getting 0 over 0? That should be the first thing. Everyone should be getting 0 over 0. Is anyone having trouble with that part? You got something bad here? So the algebra, the question here is, what algebra will you use? And Nathan, you're suggesting doing something, and I agree with you, but let's try and state it in a way that I guess it's something we can take forward with us. Like in the previous 2 examples or 3 examples, we did some factoring, right? Factoring. Then we did a conjugate, right? We brought in a conjugate because we saw square roots. Here, we're seeing something and we want to do something, but I want to make sure we state it in the proper language.
You want to combine those 2 fractions together?
Yes, we want to combine them. So what we see in front of us are what are called, this is called a complex fraction. It's a fraction with fractions in the fraction, right? And when you see complex fractions, you should be thinking, combine, get a common denominator in the numerator, right? So that's kind of like the little light bulb that needs to go off. And that's what Nathan was suggesting. The suggestion was, let's try and get the same denominator down here and down here so that we can put them together. So Nathan said, let's multiply the first fraction by 25 over 25. And then that would force us to have to do x squared on the top and bottom there. Right? And y'all see how that would give us 25x squared on both of those fractions. Yeah. So let's put those together. We'll have limit x approaches 5. Let's see, my new fraction here is 25 over 25x squared. I'm going to go slow here on this first one. Then x squared over 25x squared. All of that over x minus 5. Now, because they have the same denominator, I can put them together. I get 25 minus x squared over, that's too big, over 25x squared. Put all of that over x minus 5. Right now, is this somehow going to make things better or what? I don't.
You could then factor, because that's the difference of squares, the 25 minus x squared.
That's a difference of squares. Everyone see that? So let's factor that. Good. This becomes, let's see, 5 plus x, 5 minus x. You have to get that in the right order. Then over the common denominator. And then all of that over x minus 5. And you know what? This might be a good point for me to point something out. Okay, little side note here about algebra and arithmetic. If I write 16 divided by 4 divided by 2, what's the correct answer?
2.
2?
Yeah, you'd have to then equal your denominator with the numerator's denominator.
So if you do 16 divided by 4 first, you get 4, right? And 4 divided by 2 would be 2?
Well, I did it as more
What if you
of
did 4 divided by 2 first? Then you get 2, and 16 divided by 2 would be 8. So which is correct?
I was clearing the numerator, the numerator's denominator. So I did, you know, if it's 16 times 1 over 4, essentially, then you multiply the 2 by 4 over 1, so you get 16 over 8, and then 2.
Wouldn't you be able to just multiply the 16 over 4 by 2 over 1 or 1 over 2?
Yeah,
So,
which is
okay, so this is a trick question. Okay, I did this intentionally and I apologize ahead of time. What's that?
Can you make one bar longer so we know which fraction is which?
Thank you, Caitlin. I have to make 1 bar longer. Okay, it is improper notation for me to make both bars equal width, because then you don't know which one to do first. So I must make one of these bars longer to clarify what happens first. So by making this bar longer, now you're going to do 16 divided by 4 first. That's 4. 4 divided by 2 would be 2. So the correct answer to this would be 2. If I did it the other way and did like this, then this would be 16 divided by 2, and that would be 8. Now, the whole reason I'm stating this is that this bar right here is the big bar in the problem. So this is the big bar here. This is the big bar here. This is the big bar here, right? So we have this fraction on top of this one. It's kind of like this one right here. This will be important later. I just want to make sure there's a little side note that the length of the bar, if you have complex fraction, the length of the bar actually matters. Okay, so now at this point, right here, there's several ways to look at this. So I'm going to take it one particular way. You may or may not like this. I'm going to look at the denominator as being this over 1. And now what we have is a fraction on top divided by a fraction on the bottom. And when you have a fraction divided by a fraction, it's the same as multiplication of the reciprocal. So this actually becomes limit. That's just property of division from like elementary algebra, that when you divide two fractions, you really multiply the first one by the reciprocal of the second. So this becomes 1 over x minus 5 like that. So I just take the bottom one, flip it over. Really, I'm just kind of like flipping it and bringing it up like this. Now, do y'all see what's about to happen? I mean, it almost wants to cancel one of these, but it's not quite there. Do y'all see these are not ready to cancel?
Mm-hmm.
So how can I fix that? How can I make it where it will cancel? A little tricky here.
Don't you have to take a -1 out of it?
Take a negative factor, -1 out. Okay, from where?
From the 5 minus x.
Okay, so who's that? Samuel. What Samuel's saying is 5 minus x. If we were to just look at 5 minus x over here by itself, that if you wanted to, you could rewrite that as -1 times -5 plus x. In other words, Samuel's saying take a -1 out of this factor. Do you all agree that these are the same things?
Mm-hmm.
Okay, and then do you agree that you could even then just rewrite that this way? Just kind of change the order inside, put the x here and the -5 here?
Yes.
Yeah, so these two are equal, right? 5 minus x, or sorry, yeah, 5 minus x is equal to -1 times x minus 5. So we're going to turn this into -1 times x minus 5, and then the x minus 5s will go away. And what we're left with is limit x approaches 5. I have the 5 plus x here. I still have a -1 next to it. And then I have the 25x squared on the bottom. So remember that -1 that we pulled out over here is still here, right? The x minus 5 is what went away. And as soon as we get that canceling to happen, we're ready to roll. Let's let x go to 5 now. Let's try this limit again, see what happens. So we get 5 plus 5 times -1 over 25 times 5 squared, which equals, let's see, 5 plus 5 is 10, so we get -10 on top.
And then 625 on the bottom.
625 on the bottom. That's 25 times 25. And I think we can reduce this by 5, can't we?
Yeah, it'd be -2 over 125.
There we go. All right, so when it comes to doing these limits without a graph, what we've seen so far is we've needed some factoring. There's a problem where we needed some conjugate. Here's a problem where we needed to combine these complex fractions, combine the numerator, get a common denominator, and then start working out algebra, and then even had to do a weird little factoring of a -1 out here. So I guess the moral of the story is that, you know, the algebra is the key, right? It's what sort of algebra can you do to handle these. So let me see if there's more here. Oh yeah, there's one. Trying to see which one of these I want to do. Okay, this one, I'm just going to get it started. We're not going to work through the whole problem. If x goes to 1, do you all see pretty clearly 0 over 0? Okay, so now factor. Can you factor?
Yeah, isn't that a difference of cubes on the top?
That's a difference of cubes. So you have to remember from some class in the past that that factors to be x minus 1 times x squared plus x plus 1. Now, on your formula sheets, I believe there is some algebra reference on here. Yeah, here we go. On reference page 1 of the formula sheets you're allowed to have for the test, there's all these different exponent properties, and you know, there's lots of things here, but one of the things it does have is some special factoring. And this right here is your difference of cubes formula. So you could use that formula right there to do what I just did, right? We have x cubed minus 1, so y is 1, so you just replace all the y's with 1 and you would get what I just did. So I'm just trying to point out that the formulas, some of them are there. So this becomes, sorry, limit x approaches 1 of x minus 1 times x squared plus x plus 1 all over 1 minus x. And do these cancel?
You can do that trick we just did, pull out a -1 on the top, and then you can
Yeah.
cancel it out.
So you would have to do that little trick where you pull a -1 out. Because these are almost the same, they're just off by a sign, right? The x here is positive, here it's negative. Here the 1 is negative here and positive here. So they're off by exactly a sign. So if we pull a negative out, we should get things to work out. I'll let you take that the rest of the way. I wanted to look at this one here. This one's a little different. I mean, it just looks different. This is the first time where we have a problem where we're using h instead of x, but it's the same concept. Let h go to 0. Let h go to 0, not x. So what happens if h goes to 0 here? What would you get?
0.
Yeah, you get x cubed, right? Minus x cubed over 0. Do y'all see how this happens? If h goes to 0, let me do it this way. X cubed plus 0, or no, x plus 0 cubed plus x cubed over 0. So I just replaced both h's with zeros. X plus 0 is x. So that becomes x cubed. Oops, that's a minus in between, sorry. X cubed minus x cubed over 0, that's 0 over 0. So this is bad.
Is there a reason that it matters that it's 0 over 0 and not any number over 0?
Any number, like you mean, yes, it's very important that it's 0 over 0 what's happening. Okay. That's the bad scenario. If we got a number over 0, like let's say 5 over 0, that's a different kind of bad, and we haven't talked about that yet.
Yeah, that would just be undefined, wouldn't it?
It's
no,
actually,
no.
We're going to get something. If you go back to, where's our, let's see. I think I've logged out, but I'll show you here. This is a good time to show this to you anyway. It's 420. Let's see. Okay, so in our class, in our files for the class, there is this thing I have here called limit summary. And we're going to use this. You're free to print this out. When we just did this limit right now, what we've been doing today in this last part of the class, what we've been looking at right now is 0 over 0. Okay, and I've told you when you get 0 over 0, we're going to do some algebra or some trick, right? It turns out that there's a bunch of other things that could happen where we're going to need algebra or trick. If we get infinity over infinity, or 0 times infinity, or infinity minus infinity, or 1 raised to the infinity, or 0 to the 0, or 0 or infinity to the 0, any of these cases are going to require algebra. Now, if you have a number over 0, I think Justin, I don't know who asked, I think it was Justin asked, what if you get a number, like a fixed number, like, wait, hold on, where is it? Like 5 over 0. Or, you know, negative 5 over 0, something like that. We have a whole different scenario. And then if we get 0 on top and a number on the bottom, well, that's just the answer will be 0. And then this answer will be 0. What I'm getting at is we are just first getting a glimpse into limits. And all we're focusing our attention on right now is the 0 over 0. More to come later. All right. All right. So let me get back to that. So we weren't done with this problem, were we? We weren't done. We were sitting here, we were going, okay, we get 0 over 0 here. We need to do some algebra. So anybody have any ideas on algebra we could do with that?
It looks like a difference quotient.
It does look like a difference quotient, yes. It's actually where it comes from.
You could just FOIL the x plus h to the third.
Okay, so you could just do x plus h to the third power. Just multiply it out. That means do x plus h times x plus h, x plus h. What can you not do? You cannot tell me that's x cubed plus h cubed. Please do not tell me that this is this.
No,
Why? Because that's not the way it works, right? A binomial to the third power means you have to multiply it times itself 3 times. It does not mean you can just drop the power to each one of those.
Yeah, wouldn't you get x squared plus 2xh plus h squared times x plus h minus x cubed?
Yeah.
Over h.
I'm not sure what. Let me write down first what I would do, and then I'll just give you the answer. So I would, if it were me, I would multiply those two together first, like FOIL them out and get this. And then once I get here, I would multiply this times this, this, this. And then after I do that, I go h goes here, 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 and I get a final answer. I collect all my like terms together. So that's algebra. I'm not going to go through the steps, but I'll just tell you this is what it turns out to be. So if you were to do that, right, multiply that x plus h times itself 3 times like that, this is what you get. So if I now put that here, so everything in yellow is this, which was that. But don't forget, you still had the minus x cubed here.